Right. All right. Hey. Oh, yeah, no, this doesn't have to go online, but that's okay. These are mostly for local people. All right. So everybody, let's get settled in and get going. We have a couple of minutes before we start. Uh, just a few housekeeping announcements as usual. Again, we are lucky today. Parking is free, so if you drove in, great. It'll be good. The program for the day, today we have just one team. So after these housekeeping announcements, David takes the floor with his team and they tell us what they've been doing for the last almost 6 months actually. And after that, we will have a lunch break and then we have a few hours for the teams to go back to the lab, regroup, figure out how to wrap up things, what papers to write, so on and so forth. And then whenever you guys want, you can take a break. And at the end of the day, there will be a farewell dinner. Hopefully, this is by invitation only. Hopefully, you know you've been invited and you're coming there. Parking instructions went out if you're driving there because they have a lot where we can park for free, part of the museum, our booking. And then if you don't want to drive, the Charm City Circulator goes there from here. That's an easy way to get there. Just get off at the Maryland Science Center stop. And after that, when everything is done at the end of the day, we might do a few more things elsewhere. Right, so that is the plan for the day. As usual, the restrooms are behind you, in front of me, behind the wall. Closest dining is to our left, the Hopkins cafeteria. And then if you want to go further out to my right, about half a kilometer, there's our house, or half a kilometer that way, there is St. Paul Street. And as usual, it'll be up to the speakers to decide how to take questions during the talk, after the talk, interruptions, okay. As usual, if you have a question in the room, please come to the mic or wait for Krishita or Harshada to get you the mics, because we want the online audience to hear the questions and the recording to have the questions in them. And online audience, as usual, please type in your questions in the chat. There is almost a 30-second delay by the time everything gets through to you on YouTube. So know that your questions are coming half a minute after the speaker said whatever you're reacting to. We'll still try our best to interrupt them on time to get your question in a timely way. My colleague Paula Garcia here is watching the chat and she will take care of those. And other than that, let's look forward to another exciting presentation. Yesterday's were great. Today's is going to be great as well. I'm trying to figure out which will be better, but I'll decide after the talk. Thank you. David, if you're ready, and if you could switch us back. Thank you.
Okay, I'll just leave that. Okay, so thank you very much for coming this morning to see our team's presentation. My name is David Harwath. I am an assistant professor in the computer science department at the University of Texas at Austin, and I am the team lead for the Omnimodal Encoders team at this JSALT workshop. So I just want to introduce our team as the very first thing that I do. So we have a really, really awesome, very strong team from a wide range of institutions, as well as several people from industry. So you're going to be able to see most of these people actually talking today. I'm just going to kind of jump right into what we're going to be talking about. So the topic of our team is studying multimodal large language models. So these are models that you've probably interacted with quite a bit, seen all over the news, maybe worked with them in your research. And what's interesting about these models is that there's an increasing trend where they are starting to replace task-specific models. So where we would traditionally have built a image captioning or image classification system or a speech recognition system, and the model would only be able to do that one task. With these multimodal LLMs, we're trying to unify a whole wide range of tasks that we can do across a multitude of modalities with just one single model. And the key ingredient here is that we're going to rely upon a backbone LLM, like you would see within the text community, but we're going to be integrating modality-specific encoders for representing speech, images, video, et cetera. And so in this depiction of Quen, you can see that you've got video frames and audio, which are getting encoded by the vision encoder and the audio encoder, and then the outputs of these encoders are tokens, which would then get interleaved with text. I'm going to make one kind of terminology distinction just at the onset here. There is a little bit of a discrepancy in terms of what these tokens look like compared to text tokens. Text tokens are these discrete units that you can represent them with an integer value, whereas these are vectors of real numbers, right? So you might traditionally maybe think of these more as embeddings. They could be discretized, but just throughout this presentation, just to tell you up front, we're going to be referring to these things as tokens because the intention is that they're going to be ingested by an LLM, but they might actually be continuous embedding vectors. Okay, so the thing about these models is, as powerful as they are, the way that we build them right now is kind of ad hoc. So there's a typical paradigm or a recipe, which at a high level looks something like this. There's a lot more details in practice, but generally what you do is you start off by pre-training some encoders for whatever modalities you want to handle. So you can either build your own or you can go shopping on Hugging Face and you can download a Whisper model or a WaveLM model to encode audio, or you can download a Clip or a Dino model to encode vision, et cetera. Or you can pre-train your own. And then you can also download a pre-trained LLM, or you can train your own. And then what you do is you basically connect these things together like Lego blocks using small little projection layers called often adapters or connectors. I think connectors is a little bit less clear because people use LoRa and adapters within LLMs. So we're going to call them connectors. And the idea between there is that if the image encoder's output is 1024, but the LLM's input dimension is 2048, you need to have some sort of linear projection to match those. And then you're going to perform some amount of training to adapt the encoders and the LLM to one another. This could be as lightweight and simple as just training those linear projections, those connectors, or you could do some parameter efficient fine tuning of the encoders of the language model with things like LoRa, or if you have a lot of GPUs, you could do full fine tuning of everything. And so what we're asking about here in this workshop is, well, is this going to be the recipe that we're stuck with forever, right? Or is there something that we can do which is a little bit less ad hoc, and maybe we're going to need to understand something a little bit more about the nature of our encoders in order to do that. So I'm going to go through 3 open problems within this overall theme, which are things that we identified as a team and worked on during the workshop. So we're going to talk about the encoder evaluation problem, the specialist encoder problem, and the non-text tokenization problem. So I'm going to go through each of these in detail over the next couple of slides. So the first thing I want to cover is the encoder evaluation problem. When you go shopping on Hugging Face, you are confronted with a huge number of pre-trained encoders that you have the choice of downloading. And it is not immediately clear which ones are good and which ones are bad, especially in the context of integrating them into an LLM. Maybe somebody reported a word error rate for a language that you care about working on for Whisper, and maybe they did that for WaveLM, but that's not the only thing that you're going to use your multimodal LLM for. You're going to have it be, recognizing sound events and doing speaker diarization and all kinds of other things. So it's a very kind of task, like open-ended, problem space that you're expecting this model to work within. And so outside of, that word error rate number that you got for Whisper, you don't really have any knowledge of how well this model is going to work for encoding audio to do anything else. And then something similar, a similar story holds for all other modalities like images or video. So if you don't know which image encoder or which audio encoder you should use, the easy answer is you just pick a couple based upon vibes or whatever, and you hook them up to the LLM, and then you train the whole thing and you kind of hope for the best. So this is an extremely time-consuming, extremely expensive, extremely wasteful paradigm of doing this kind of evaluation, right? Because we all know how difficult it actually is to train these large-scale models. So what we're asking is, well, can we do something better? Can we find a lightweight evaluation paradigm, a way to kind of stress test encoders in isolation without having to do this heavyweight, large-scale training, with the intention that these lightweight evaluations are going to be predictive of how well that encoder will do when integrated into a LLM and tested on a wide range of tasks. So the idea is that you've got some sort of model library, an LLM, and some candidate encoders. You take those encoders and you get some lightweight evaluation metrics from them, and then you see if those things are predictive of what you would have gotten if you had actually taken those encoders, hooked them up to the LLM, done lots of large-scale training and evaluation. The next thing that we looked at is the modality specialist encoder problem. So most of the off-the-shelf encoders that you're going to encounter were trained on only one modality, such as audio or video, and often on one domain within that modality. So lots of audio encoders are not general audio encoders, they're a speech encoder, or they are an environmental sound encoder, or they are a music encoder. And these things are separate models trained completely differently with different capabilities. These encoders are also generally not aware of one another, either during pre-training or when you actually hook them up to the LLM. So if I took a whisper encoder and a dyno image encoder, the output embeddings from these models are not necessarily going to be aligned with one another, or they're not living in the same space. It's not clear how easy it's going to be for the backend LLM to start to integrate information across both modalities at the same time, because these things were trained in complete isolation. And not only were they trained in isolation, but when we encode a video or an audio signal, we do that just one by one, and then we concatenate them together at the end and say a prayer and hope for the best. These current encoders are also generally pre-trained on specific tasks that are then further going to implicitly privilege some types of information. Right, so it's not only that you can have an encoder which is only good for speech or only good for music, but you could have an encoder which is a speech encoder, but it was only trained for ASR, and so it actually may not do a good job at other tasks like speaker identification. And so we're trying to address this problem of how can we build encoders that are not only good for multiple tasks within a modality, but also multiple domains, and potentially even having a monolithic encoder that can work for all modalities. So we're going to be showing today several different approaches that we've developed for addressing this problem. One of the themes that we're going to be looking at is doing joint training of multiple domains or multiple modalities together within one shared backbone, and looking at whether we can actually share parameters with sort of general knowledge blocks and having then expert-specific blocks. So we'll look at how well that works, as well as we're going to look at disentanglement of speech versus natural sound and things like that. Okay, so the last problem that we're going to be looking at is the non-text tokenization problem. So text tokenization is something that's relatively well understood. It's not that difficult to do because text is already kind of almost tokenized. I mean, if you just split on white space, you get word tokens, and it's not BPE, but it's not too far removed from that. But when you use pre-trained and audio and image encoders, the story is very, very different. So you're just automatically going to inherit whatever frame rate or tokenization scheme those models were trained with. So a model like Hubert or Whisper is going to be natively operating at 50 hertz. Other encoders may operate at 100 hertz or 25 hertz. Your vision encoder may have been trained with 8x8 patches or 16x16 patches. If it's a video encoder, maybe it operates at 10 frames a second, maybe it operates at 30 frames a second. It's just the Wild West, and it's all over the place. And so, different tasks actually can benefit from and use different resolutions. If you're doing ASR, maybe you do want to have tokens which are aligned more or less with subword units. But if you're doing speaker identification, maybe your tokens can actually represent entire utterances or multiple utterances. If you want to do object segmentation within an image, maybe you do want to have fine-grained detail and look at patches. But if you're classifying a scene, maybe you want to have tokens that represent larger pieces of the image, or maybe an entire image, or even sequences of images throughout a video if you're doing action classification. So we're going to be looking at whether we can learn tokenization schemes for continuous inputs like audio and video that are going to maximize the performance and the tasks we care about, but also minimize the number of tokens that the LLM needs to process, because tokens are very expensive. Anybody who's been using Claude throughout the workshop knows you can easily run out of tokens within your context window in just a couple hours of work, right? And as Roger's going to be showing you later, the number of tokens that you need to represent an audio waveform versus a text transcript of that waveform is more than an order of magnitude in the difference. Okay, so the outline for today is going to go something like this. We're going to be covering each of those 3 sections that I just mentioned, and we're going to be having short 5-minute breaks between each one. So we're going to start off by having Pavel, RJ, Lin-Yang, and Sandra talk about evaluation. We'll have a short 5-minute break, and then we'll come back and we'll have Chinro start with, this is incorrect. We're going to have a 5-minute break here and a 5-minute break here. We're going to talk about multimodal encoder training. That's going to be Chinro, RJ, Jessica, Zihao, Deb, and Lin-Yang. We'll have another 5-minute break, and then we'll have Roger, Krishna, Sihan, Karen, Matthew talk about tokenization for continuous inputs. And then we won't have a break after that. I'll have a small section at the end where I'm going to be talking about analyzing encoder-free LLMs. So what we ask is we're happy to take clarification questions and things like that during the presentation or at the breaks, but any sort of larger, higher level discussion-based question that could turn into something very, very interesting, we've allocated about 30 minutes at the end for that. So we're going to save big discussion questions for the end. Okay, so with that, I'm going to have Pavel come up, and he's going to be talking about the evaluation pipeline we developed that unifies all the different work packages of the team and ties everything together. Thank you.
All right, good morning, everyone. I will begin by repeating, just echoing what David said, and again, talking about this distinction in lightweight and heavyweight evaluations. What do we mean by that? Basically, everything that has an LLM in the loop is expensive. It's expensive for 2 reasons. One, GPUs, obviously, but the second, even if you had infinitely many GPUs, you would still need to wait for them to run and finish the work in some time. So in practice, you sometimes need to wait for 1 day, sometimes even 2 days, just to get a single number. This gives you very long debug cycles. What you want to do instead, especially if you work on encoders and different variations of encoders, you want to have short debug cycles. So you want to be able to evaluate them faster and get responses sooner before you go to the LLM. So what options do we have for lightweight tasks? There exists a whole array of very similarly named benchmarks that cover different modalities. They often combine something with text. There are also less wider known benchmarks that focus on predicting brain signals. And there are also tasks that are not about predicting at all. It's about analyzing some geometric properties of the encoder outputs. So in my part of the presentation, I'm going to focus on this set, but you will probably hear about other benchmarks from more folks later today. So this is a selection that we made. We selected 2 task families from the MSAB benchmark, clustering and classification. The details here are not super important. Clustering is you get your encoder outputs, you cluster them, and then you ask yourself, how well do these clusters separate labels if you have them? Classification is basically linear probes, right? Maybe more importantly, I want to point out there are, can you see my pointer here? Yeah. There are 3 different types of data in each task. Bird set is recordings of birds, FSD 50K is something like audio set. It's different sounds that are annotated by what is in the audio, and SVQ and speech massive are 2 very large collections of spoken language. Both are multilingual. I think it's like over 20 languages in SVQ, about maybe 12 languages in Speech Massive. So each task family is an aggregation over something like 30 different data sets. What about other modalities? There are more options to choose from. Clearly, for benchmarks that include text, audio, and image, you could look at OmniBench. There is text image benchmark called MMAU Pro, and we did that as well. We set up the experiments and got some initial results, but we decided let's focus on audio for now, make sure things work as we want, as we intend, and then go back and get a broader coverage of modalities. So for the audio setup, we're going to be training on Audio MCQ, this collection of multiple choice questions, and test on MMAU Pro, which is a collection of different types of questions, but the majority are also multiple choice. Here's an example from MMAU Pro. I just want to kind of nail down an important point, why it's a good task. This is a question that you cannot answer correctly if you don't listen to the audio. And this is the whole goal of this benchmark, is to make it such that you really need the audio to answer the question correctly. I mean, you could guess, but this gives you something like 25% accuracy. You really want to do better. So for the heavyweight evaluations, we came up with this recipe that combines the models like this. There's a diagram on the side. The encoder and the LLM are frozen. What we train is the adapter network and the LoRa. We also have to take care of pooling such that the outputs of all encoders operate at the same rate so that the comparisons are fair. All right, so we did this. We started running heavyweight evals. We got an accuracy of about 40% on MMAU Pro, which suggested it's reasonable, it's not bad. I mean, you could also ask, is this the best recipe? Probably not. You could spend 6 weeks working just on optimizing this recipe alone for one encoder, and then spend 6 more weeks optimizing this for a second encoder. So it's more like one thing that works sufficiently robust on all encoders that we tried. So 40% sounded promising. We wanted to verify, so we went to the MMAU Pro website, where there's a leaderboard that shows you how other models are doing. And we thought, well, we're in a good company. Like 40%, these are models of comparable size, maybe even larger. So let's get going. So we talked about heavyweight evals, lightweight evals. The whole goal of this is to see if we can predict the performance on heavyweight evals by not running LLMs, by looking just on the at the lightweight evals. So these plots are going to be showing you something like performance on clustering and classification. The higher, the better. On the y-axis, this is going to be the performance on the heavyweight eval. The higher, the better. So what do you want to see in this plot? Ideally, you would want to see something like a diagonal, right? The better you classify, the better your performance on question answering is going to be. The better you cluster, the better your performance on question answering is going to be. So here are 12 points, 12 different encoders. Blue encoders are off the shelf, pre-trained encoders from Hugging Face. Red are encoders trained by our team. It doesn't look super convincing, right? You look closer, you try to calculate the correlation coefficients, and they're all like not really super convincing. And yeah, there's Pearson's R that is statistically significant, but it's negative. The worse you classify, the better you are at question answering. This does not check out. So, I mean, we dig deeper, we see if MMAU Pro is maybe just too difficult for this setup. MMAU Pro consists of something like 5,000 questions, which are broken down in different categories. So we thought, what if there's like one category that drags everything down, and maybe we're doing better on other categories? As one does, we look at every category and we find 2 that are actually well predicted by our lightweight tasks. So I want to pause here, and I want to ask a question to the students. So Sanjeev, don't answer. There is a name for that. There's a name for what I'm doing. What's the name? Somebody said it. It's p-hacking. It's textbook p-hacking. Don't do that. I mean, you can do that. Don't publish it. Don't try to sell it. Don't show it to people and say, look, correlation, positive, great, statistically significant, right? You look at something like 12 categories and you pick out 2 that work best. That's p-hacking. So if that's what the plots would look like, everything would be amazing, right? But that's not the real story. And I guess the cautionary tale here is, let me say one more thing and then I'll get back to this in a second. So ablation, very good point. If something like that happens to you, you want to understand what exactly went wrong. So one obvious ablation is what happens if we ask the model the question, but we don't give it the audio. And one way of doing it is you replace it by silence, just replace the audio samples by zeros, or you replace it by noise, same idea. So with real audio, you get different values around 40% accuracy with the encoders that we trained. So what do we want to see ideally in the other 2 columns? Something much lower, right? 25% would be a natural floor for multiple choice questions. It doesn't go down, sometimes it goes up. So apparently this is actually known behavior, and the authors of the MMU Pro commented on this in the paper, which I did not see in time. Turns out they knew that this is a property of the data set. So there are questions that you can answer without listening to the audio. And because the noise floor is so high, the experiments that I ran with heavyweight evals are barely above this noise floor, almost indistinguishable. So let me wrap up just by saying that getting the heavyweight evals right is a hard problem. Partly this is because the problem is hard, the evaluation task is difficult, but also the recipe, getting the recipe right, getting all the parameters, meta parameters right, takes time. On the other hand, lightweight evals are easy and probably bug-free, more consistent compared to something that involves training of models with LLMs. So cautionary tale I wanted to mention here, don't run ablations on the last day of the workshop. Try to get them in as early as possible. We have first model ready, see what it does if you give it noise, see what it does if it gives it silence. It might tell you something that you did not expect. All right, let me wrap up and hand over to RJ and Lin Yang. They will be talking about a different type of lightweight evals that involve a prediction of brain signals using encoders of modalities that we're talking about.
So there was this very interesting paper from Stanford, I'm sure you've seen it, called the Mirage of Visual Understanding, where they showed that you can do excellent work in X-ray image understanding without even showing the X-ray images. It was in the news a few months ago, and it was big news. This is it's very related to what you said.
Thanks for the comment. I didn't see I wasn't aware of this paper, but apparently there's one thing that everyone can maybe use as a takeaway. If you publish something like a leaderboard, add those rows to the leaderboard. Have it publicly visible. No input, zero input, silence input, something like that. All right. Sorry, Ajay. Over to you.
Right, so like Pavel alluded to, I looked into whether we can use brain data as a potential lightweight benchmark for multimodal encoder evaluation. And of course, the intuition for this is that the brain is the world's best multimodal encoder in the sense that it can process information from many modalities, far more than the ones we use right now, all in a fraction of a second using far less energy than we use in our artificial multimodal encoders. So if we can make things more like the brain, that's probably a good thing. So the idea we had was for using brain data as a sort of comparison standard for the quality of a multimodal encoder. And so to do that, we just need to observe a few simple facts about how the brain works. So first and foremost, we'd like to note that the brain's response to external stimuli is this learnable and quantifiable function in the sense that when a person sees a particular stimulus, when they're exposed to some stimulus, their brain responds to that stimulus in a relatively deterministic way. So if you show it to them again, most of the brain will respond in an identical way. And so we're going to be doing this benchmarking by using a kind of model called an encoding model that tries to model this function between stimulus and response that is moderately deterministic. And since we're studying multimodality, we're looking at a multimodal task that humans did while they were being scanned. So in this case, they were in an MRI machine while they were watching the TV show Friends, which, as we know, has audio and video. So they're engaging both of these modalities at once. So the way these models work is very simple. First we take our stimulus data, which is again just this TV show Friends, which you've probably seen, and we feed it through some embedding model M, which can be either a unimodal encoder or a multimodal encoder, and that gives us a set of features. And then we learn some linear mapping beta that projects these features from the multimodal model onto contemporaneous brain data that we collected. And this gives us some final held out prediction on our held out test set. And in order to measure how we did, we just correlate the ground truth measurements on this test set with the predicted measurements. And that gives us some correlation score, which we call the encoding performance. So here was the first result that I collected during my time here, and this was to simply perform this brain evaluation on as many unimodal and multimodal encoders as possible. So each line here is a single encoder like Whisper, Quen3 Omni, or Siglip, and each color here represents a different kind of modality. So the green here is a standard text LLM, the brown and purple are the video and image encoders, and the blue is audio encoders, and then of course at the top, the red is the multimodal encoders that can accept any or all of these modalities at once. And what we can see broadly is that the multimodal encoders do better than all of the unimodal encoders, which is hopefully what we would expect for some sort of multimodal benchmark. So check one thing down. And this shows that data in a slightly different way. So I've plotted the peak encoding performance for each of these encoders across all of its layers against the number of active parameters being used in each model. And we can see that at least within each modality, the performance.
What is on the y-axis? Can you just elaborate a little bit?
This is the encoding performance benchmark that I mentioned. So we have like 1,000 parcels of like little chunks of the brain. For each of these parcels, we get a predicted time course over the course of the episode for every episode in our test set. And we have the actual time course of the activity in that parcel. And we just correlate those two. And that gives us our encoding performance metric for that parcel. And then we average over all the parcels. And that gives us a single number. We believe, not due to experiments done on this particular data set, but on other data sets, that we were pretty still far off from the noise ceiling here. So we think that we could get a lot better, actually, as high as 0.3 to 0.35.
Okay, so that does lead me to the second question. You said earlier that the brain is relatively deterministic in the sense that the same input will produce the same output. What I'm thinking is, in the Friends data, sometimes in the show, for example, a short scene is used earlier in the show just to sort of preview what's coming, and then the same thing shows up again. Is it possible to take like a 1-2 second chunk and check between those two responses what these coefficients are? Because what I'm thinking is 0.3 good or 0.22 good or bad? And I'm thinking, how much is the brain signal itself correlated to 2 episodes of the same?
Yeah, this is exactly right. So this is a very sharp point. So this is usually what we do on data sets that have lots of repeated data. This doesn't have a lot of repeated data. There are these isolated segments. I didn't take the time to segment them out. But yeah, so you can do exactly that. You can do a noise ceiling analysis, and this gives you like an estimate on how high you can go. We don't think we're that far off from how high you can go. But but it's not one. The ceiling is not even close to one. I said the brain is mostly deterministic, but there's also lots of parts of the brain that don't respond to stimuli at all. And those things are just zero. So keep in mind that this is like an average over 1,000 parcels, that some of which don't do any kind of sensory processing.
Can I do another question? You do per frame correlation, right?
Actually, we take the whole episode, so we get a time course over each episode for the parcel, and then we have the measurement, which is also a time course. Then we correlate those two, and then we average over all episodes and then over all parcels. Yeah.
But that assumes that there is some alignment frame level from the features to the brain signals, right?
Yeah.
Maybe it's difficult that they are temporally aligned precisely. And I don't know, did you control, like, for example, for the feature size of, like, depending on the pooling, for example? Because I expect that if it's more coarse, the output features.
Yeah, if you use random Fourier features, for example, to do this prediction, so they're like features that have high dimensionality, but don't actually have really any deep embedding of these modalities, you do terribly. So like you'll get like 0.001. I mean, you'll get some value. Like you won't get zero, but you'll get way lower than what you get if you put it through these modalities. Yeah.
Okay. Because you try to do some cross correlation, for example, to the alignment.
If you also misalign them, you do poorly.
Yeah,
okay,
exactly.
Okay. So you do. This is
here,
actually
for
hard
example,
to do.
you take the peak, right?
Right.
Only.
Right.
Here you take only the peak.
Here, this is just the peak of this on the layers, not on the time courses. Yeah. So, sorry if that was unclear. Yeah. So all I was going to point out here is you guys got through most of it, but it also obeys some nice scaling laws, which is again something we might like to have in our benchmarks. It kind of makes sense. So it's another sort of check mark. So given that I have shown you that this is a sort of well-behaved benchmark and that it aligns with our objectives for it to be a multimodal benchmark and that it's also not entirely trivial, the question remains whether it's actually a useful benchmark in the sense that Pavel mentioned before, in that it's a good predictor of the downstream performance and other tasks that we'd like to actually have our models do for us. So to test this, I evaluated 16 of these models. These are Qwen-based models. I evaluated their performance on both the brain prediction task and then a handful of 3 different video benchmarks. So this is an action classification benchmark, an emotion sentiment benchmark, and then an audio-visual pairing benchmark, and then I just composited their z-scores to a single unified video benchmark here. What we can observe is that at least on these video tasks, there actually does appear to be a fairly good correlation in that the brain prediction performance significantly correlates with the composite of these 3 video tasks. So at least it seems that this brain prediction performance metric is a kind of meta benchmark for embedding of videos at the very least. Now, there's a bit of a caveat here in that we also did the same experiment for audio tasks, and unlike the composite video tasks, we don't observe a correlation here. We're not exactly entirely sure why this is. We have some hypotheses. We think maybe part of the reason is that there's a lot more room for improvement in our video embeddings compared to our audio embeddings. So maybe there's a wider gradient here. It's easier to sample from. That being said, the verdict here on why this happens is still out, and we need to do more work here to understand this phenomenon. So now we're going to move on to Lin Yang's presentation. He has some stuff to talk about regarding SEEG data, which is a different scanning modality for the brain. So please, Lin Yang.
Yes, so as RJ just mentioned, that so far we've used fMRI neural prediction as a lightweight way to evaluate multimodal encoders. Here we look at a complementary neural signal SEEG or stereo EEG, which is a type of like intracranial EEG data. So the main advantage of SEEG is temporal resolution. fMRI reflects a hemodynamic response over seconds, while SEEG measures electrophysiological activity at a millisecond scale. So this is particularly useful for speech, where acoustic, phonetic, and lexical information evolves very quickly over time. So we use a data set called Brain Tree Band. It covers like 6 subjects, more than 900 electrodes, and about like 3,900 sentences clips from natural movies. So this data set was released by MIT and the Massachusetts General Hospital. So, and here's like the encoding pipeline we use for all of the speech encoders. So for each movie sentence, we extract layer-wise encoder features and align the frame level representation with time-resolved high gamma activity. So we reduce every layer to like 256 dimensions with PCA, and then fit the same region regression model over neural lags from -500 to +1,000 milliseconds. So evaluation uses like 5-fold cross-validation, and the feature scaling PCA and target normalization are all fit only in the training folds. So the final score is like the head-out Pearson correlation between like the reconstruct neural signal and the original neural signal. So because the readout and the evaluation protocol are fixed, the differences in the R score are many reflect differences in the encoder representations. So here are the temporal and layer-wise results. So on the left, we look at like the performance as a function of time lag. So all 5 encoders peak at like positive lags, roughly 80 to 300 milliseconds after the onset. But like the peak time differs across models. So Quinn Audio Tower peaks relatively early. Beats is around like 160 milliseconds, while the other 3 peak much later, around like 320 milliseconds. So on the right, we have like we look at like which layer gives like the strongest neural prediction after normalizing layer index by model depth. So again, these models are quite different. So Beats peaks relatively deep in the network, while several other models peak much earlier. So the main point here is that neural alignment is selective both in time and in network depth. So so 2 models might have like a very similar average score, while organizing speech information quite differently internally. So here we look at like where these encoding scores come from spatially. So for our 4 strongest audio encoders, we plot each electrodes using the model's selected layer and the peak latency. So within the same, as we can see, the strongest positive correlations are concentrated around like the superior temporal or auditory region. So the overall spatial pattern is pretty consistent across all 4 speech models. Yeah, so also I need to mention that the SEEG coverage is like clinically determined. So like as you can see, we don't have like much like visual coverage here. Yeah, so we should now interpret this as like the population level brain atlas like fMRI. So by the coverage suggests that, by the convergence suggests that the encoding score is like largely driven by speech responsive clinical activity rather than like a home brain effect. So we also compare like the SEEG encoding results with the downstream benchmarks. So we leave out like Quinn Audio Tower here because it is like a off-the-shelf audio tower from like larger multimodal model rather than like a standalone audio or speech encoder like the other 4. So once we focus on like these 4 speech or audio models, the relationship becomes like much clearer. So SEEG alignment tracks like both the lightweight MSEP score and the heavyweight MMU Pro score. So for MSEB, the Pearson R and the Spearman rho is relatively high, I guess, and for MAU is like around 0.7, 0.8. So across the very small set of models, models that better predict neural responses also tend to perform better on like conventional audio benchmarks. But with only 4 models, these correlations may be not very stable. So I would treat this like preliminary evidence rather than like a very reliable model ranking results. And we need more like encoders before making a stronger claim. So with that, we've looked at like neural prediction as an external evaluation signal. Next, Sandra will ask whether we can get another useful signal purely from the geometry of the embedding itself. Yeah.
All right, so thanks, Lingyan. I think we've heard a little bit about heavyweight evaluation being expensive. And for this part of the workshop, we wanted to give it a different perspective on using mathematical and geometric analysis to see if we could uncover anything interesting about how these models are learning and about the latent representations of these models. So from this perspective, we thought about an intrinsic metric as an evaluation metric that could be, or that could offer us 3 things. First, that it could be task independent to help us describe how the model is capturing information without being tied to that specific task. Second, perhaps label free, that would be awesome. So we don't need to rely on those downstream labels and we just focus on using those latent representations. And third, being flexible. So can we use any encoder that has its hidden states exposed and use this metric as a proxy? So in our case, we found that local intrinsic dimensionality is a candidate to some extent, and I'll go through the results in a second. This metric has been used for anomaly detection, and we've used it as well in speech for that particular purpose. So you want to see, well, does this extend to other models, not just encoder-only models, but also decoder models? And does it provide any insights on whether we can choose certain models or train better models? So I won't go into the mathematics of what this metric is, but I thought I'd give a little visual intuition around what this might show us in high dimensional spaces. So we've got here a diagram showing 3 unit spheres from left to right. On the first one, we've got points on a line showing an intrinsic dimension of 1. Then we follow all the way to the right at dimension of 2 and 3. And what this really is providing, LIT is providing, and by the way, LIT is not a language ID. Just thought I'd clarify that as well. So this is providing a mechanism to measure a number of coordinates. In this case, we care about those dimensions. And again, we're wondering whether this is useful as a way to capture the information that's been represented in our data by these models. One thing I'd like to highlight is that unlike global metrics, which some of us have also used in other analysis as part of the summer, LIT captures the localized geometric complexity that could vary across different regions of a data manifold. And so this could reflect that perhaps in lower dimensional surfaces of these topologies, there are hidden information that is embedded within a high dimensional space of the data where it naturally lives. So we continue this work as a mechanism where we asked whether LIT could help us address the following 2 concrete questions. So the first one, we focus on layer-wise across a model's layers. Does layer-wise LIT track representations that align with downstream performance? That was the first question. And the second one is more across models. So this was a bit more of a stretch. Can it help us correlate? Can LIT help us correlate with benchmark scores? And as Pavel mentioned, MSEP was one of those interesting evaluation benchmarks. And so we want to have a quick look at 2 models. So we've chosen GEMMA 412B, which is just it's an encoder-free, only a decoder model, and Whisper Large. And so now I'd like to now dive into some of the results. We'll go into like 3 layers because I'm aware there are a few plots on there. But feel free to ask questions afterwards. So they're not strongly conclusive, but I'll walk you through it. So some of our results here are shown. So on the left-hand panel, we've got the Whisper Large results. On the x-axis, we've got the layer depth. And so, and then I've normalized this in terms of set score so we can actually compare the local intrinsic dimensionality with the overall performance across different tasks. And on the right-hand side, we've got the GEMA for 12B also being analyzed. One of the things that we were interested in, it was, well, can this actually help us determine what's the best layer? And actually, no, not very good news on that. We were not quite successful on that. But it does provide some interesting interpretations on, so like here with the teal colors, we see shaded regions that correspond to a positive correlation. So that means that as the score rises, this is where lead rises as well. And then on the purple side, we've got the negative side of the correlation. So if the score rises for a specific downstream task, the lead actually drops. So it's a negative effect. So I'll go now into the more broad set of results. On the top quadrant, we've got, again, results for Whisper across a subset of tasks for MSEP. And these are all particularly focused on audio. And one of the things we observe is that it's not always positive or negatively correlated, but the overall geometric and representations kind of flow throughout consistently throughout the first top of that quadrant. Then we also see the GEMA results, where performance is highest, where lead is lowest in general. And we do see some, I guess, distinctions where that doesn't really align to the trends we see on the other ones. So one thing I wanted to mention is that this is some ongoing work. We do see that for clustering scores, there is a similar trend and perhaps a more consistent one for this subset of tasks. But given the time frame, we are aware that we need to look into this more closely and expand the analysis to try to understand what really is happening here. The main takeaway is lead can be a useful metric to use in parallel to other of the metrics that we're using throughout this workshop, but it shouldn't be used as the metric that will tell you choose the best layer. And it will not tell you, at the moment at least, it will not tell you whether it will align with your downstream performance. So we're not disregarding it, but more work needs to be done. So yeah, please ask me questions if that was too much information on here. But I will now pass it to Pavel, who will share key takeaways from the encoder evaluation portion of this team.
All right, so in this section, we looked at two types of evaluations, heavyweight evaluations that involve LLM that didn't go as planned. We looked at different types of lightweight evaluations, and we can broadly put them in three buckets. One is something that tries to assess the separability that encoders provide in terms of how well the classes inside the dataset separate after the encoding. We heard from Lin Yang and RJ on how we can use brain signal prediction as a proxy to see how well the encoders encode all the different modalities. And we heard from Sandra on how to measure this geometric structure called local intrinsic dimensionality to try to understand what is happening in each layer inside an encoder. As a reminder, as David pointed out, we have 4 sections. So this concludes section 1. In the next section, we will hear from the team that was in charge of training all the novel encoders, so way more interesting things to come. We will have a break for 5 minutes, and then we'll return and hear more from Jinro. Thank you.
Hello, guys. It's time to come back. It was meant to be just a 5-minute break. Hello, hello, hello. It was meant to be a 5-minute break, so please come back. So we don't have Najim today, so we won't do one of those loud "aye" kind of things, but yes.
Okay, so while people are getting back to their seats, we're not going to actually start flipping through slides yet or anything. I'm just going to give you a little preview of this next section. So what you just heard about from Sandra and Linyang and RJ and Pavel is about the overall evaluation framework and harness that we developed that kind of unifies all the different encoders that the different subteams of our teams or the different subteams of our overall team were building. So you may have noticed, as Pavel pointed out, that in his correlation plots, there were some blue dots and then there were some red dots. So those blue dots were these baseline models like Whisper and Beats and WaveLM that you've probably heard of. And then the red dots were all the different models that other parts of our team developed to measure against those other baselines within our evaluation framework. And so now we're going to move on to the portion of the talk which describes these new models and how we went about building them. So to start us off, we're going to have Chinro talking about learning disentangled and unified general audio and speech encoders. So Chinro.
My project is about like how to unify the different type of information within the same modality, which is audio. So I guess most of you are all familiar that we used to have different types of encoder for different aspect in audio. For example, we train speech encoder with speech dataset, audio encoder with audio dataset, and same for music. But so the good thing for this is that these we can analyze these encoders to see whether they specialize to their specific domain, and they can capture these type of information more efficiently. But the downside for this is that when we want to wire them into language model or some more wider range of downstream tasks, we need to have different types of encoder to do, like we have to combine them together to do all of them. And that's why people start to move through the direction where we have a more generalized unified encoder where we just merge all the data sets from different domains together and then use the single encoder to do everything. And this is a type of encoder that we often see nowadays in multimodal language models, and also some new distilled models that we're gonna be talking about. So one of the questions, so these type of models can handle like speech and audio pretty well, but the question is that when these different type of information are overlapped together, are they still able to like be aware of them, or are they going to be confused? And this is quite an important question because most of the scenarios in real world situation, we have them overlap together instead of separate clean streams. And to inspect this, we are using this model called USAD 2.0. So this model basically uses distillation to learn from already trained teacher models that are good at different type of domain and try to compress everything into the single model. And it comprises of 2 stages of training. The first stage, it uses unsupervised teachers to try to initialize the model where the lower layers would look like the lower layers of the teacher model, and then the later layer would look like later layer of the teacher models. And then in the second stage, they switch to stronger supervised teachers, and then try to like make the model also learn these information from them. And then for the data set, we constructed a new data set that includes these kind of overlapped speech and audio information with a FastMMS toolkit. So this is how the example in the data set might look like. So within the same audio, we have the speech, which sounds like there are multiple speakers doing a dialogue from an ASR data set. And at the same time, we have the audio events at the background. It's random places in the audio. So yeah, I'm not sure if I can, okay. Well, like, it's fine. The first example will be like, you can hear people talking and there's people pouring water in the background. And the second one, you can hear there's music playing in the background, and sometimes it overpowers the speech part. And then with this dataset, since it's generated from ASR and audio caption dataset, we do have another annotation that we can do like interesting stuff. For example, we can do the like ASR, speaker identification, and also the audio captioning or classification tasks with this. And apart from that, we built the dataset that's we built an evaluation dataset on them to see how the models are disentangling these different type of info. So the evaluation scheme here is similar to what Pavel has mentioned, the heavy eval part, where we have an encoder, have a language model, and tries to connect them together and see how well they perform. And there are 3 types of queries included in the datasets that corresponds to the task like I've mentioned. So the content for ASR, speaker, and then the background noises. And since usually when people connect the encoders to a language model, we just take the final layer we just take the final layer because we usually think it's the most informative one. But is that really enough? So we conducted the preliminary experiments on it, and the number I'm reporting in my part will all be the accuracy on our MCQ datasets, where the columns over here corresponds to the task that I've mentioned. So the content, speaker, and the background. And then the config here, the first row will be where we just take the final layer of the model. The second row is where we combine the layers from different depth of the model. And so if we compare first row and the second row, we can know like whether the model already have everything in the final layer or there's still something missing there. And then the last row is a top line where we fine-tune the model on these 3 tasks to see like whether the pre-training is missing something or there's already enough information. And then we give a score breakdown of different SNR level. So when the SNR score is low, the background noise is higher. So we would expect that the content questions will be more challenging. And on the other side, when the SNR level is high, we'll think like the background noise questions will be much more challenging. And here are the scores. So basically, we can see that if we only comparing the first 2 rows, combining the model's information from different depth will give them an advantage on the challenging cases that I've just mentioned, which is like the underlined examples over here. And there's not that much of a difference between the combination method here and the 3, like the version that we fine-tuned. So the small conclusion here is that the information is already somewhere in the model, but we only take the final layer. It not be that good. So that's why we move to the next stage and think like, what about we just continue pre-train the model on the overlapped data set that we have and see if the performance can improve. So the figure here is a small recap of how the model is trained. Basically, they have different teachers trained on the same set of data sets that are separated speech, audio, and music. And in our stage 2+, we continue the training setup of stage 2, but then switch to the speech and audio overlap data sets and see like how the model can improve. And another thing we do is that we take a step further and think like, what about we give the teachers different views of the data? So for the speech teacher, we give them the speech, and the general or more audio-focused model, we give them a background and see whether the students can sort of disentangle these information in the layer embedding that they learned. Okay. And for here, we compare the results. So the dots are the accuracy of the content queries, the squares are the background queries, and the different colors corresponds to the model that I've mentioned. So the gray one is the stage 2 in the middle. The purple one is the one that we trained in the same setup as gray, just switching the data sets. And then the blue one is where we let teachers take different views of the audio input. So if we look at the more challenging case, we can see like when the SNR is low, and on the content side, continued training, which is the colored one compared to the gray one, usually have a performance increase. And for the background noise setup, we also see the same trend where continuing training with the mixed data sets give a slight advantage over the one without training with it. And the next thing we want to see is whether these training, like how do the student model compare to the teachers. So one thing to note is that the teacher models are usually larger, and for the rows, we have a plus sign over here. We simply just run inference on each of the teacher model, concat their embeddings together, and pass it to a language model. So they are much larger in parameter size compared to the students here. And so we can first, like stage 1 and stage 2 teacher are the teacher that I illustrated in the figure before. So if we are only looking at the teacher, it's kind of slightly surprising to see that the stage 1 teacher actually performs slightly better than the stage 2 teacher on all the aspects. And if we're only looking at the stage 2 teachers, where we try to only use a speech encoder, a more audio focused encoder, and concatenate them together, the performance doesn't really actually differ that much. And here, if we focus on the challenging cases, where like trying to find the content when things is noisy, or trying to find the background when the speech is stronger, we can see like if we fine-tune the model further with the overlap data sets, we can have a slight debump of the performance. And that's, so some of the key takeaway here is that the unifying the encoders together will give us advantage on the flexibility and the efficiency over the specialized encoder. And then not all information propagates to the final layer, especially when there is more domain like speech and audio involved together. And then the last thing about data is that multitasking on instance level beyond just dumping the data set together might be a gap to explore. So my part mostly cover like how to unify the speech and audio into one. And then I'll pass it to Jessica about how to unify all the different modalities together. Oh, RJ, oh, I'm sorry.
Hi, everyone, again. Earlier in the talk, if you weren't here, I discussed this idea where we could use brain prediction as a sort of meta benchmark for our encoders, and especially worked well on our video encoders. And now I'm going to discuss something sort of related along the same lines, which is this idea that we can actually use the brain data directly rather than just using it for evaluation. So we're going to actually train on the brain data now to improve the encoders. So I'm going to do that, but before I do, we have to actually decide on the brain regions that we're going to train on. We don't just want to train on the entire brain. And the idea that we had for this was to only train on the most multimodal regions of the brain. So we have to identify those regions, and so we came up with a process to do that. I'm going to explain that process to you now. So the idea here is that we are going to mathematically define multimodal brain information as the component of the brain signal that cannot be predicted from any single modality on its own. So this definition requires there to be some degree of synergy across modalities. So in that each modality needs to know what the other modality is doing to effectively make the prediction in these regions. So for a given pair of modalities, such as audio and video, in order to quantify this synergy, we're going to do a kind of variance partitioning. So we're going to create two of these encoding models. So model 1 is going to be generated by concatenating the embeddings from two unimodal encoders, one for audio and one for video, and then training our linear probe. And this model is intended to capture all of the unimodal information that can be predictive of the brain signal. And model 2 is going to do exactly the same thing, except now we're going to have multimodal encoders, and they're going to be able to look at the other modalities. So they're going to be able to be contextualized, well, video contextualized on the audio, and vice versa, audio contextualized in the video. So this model is going to contain both that unimodal information in model 1 and also the synergy that you can't get without peeking at the other modality. And then to isolate this synergy, we're just going to subtract the performance of Model 2 from Model 1. So that's going to remove the unimodal information from Model 2 and only leave the synergy. So the last time I presented this, I was told it was very confusing, so I made a few figures for this. So this is Model 1. So here we just feed in the visual information, we get some features. We feed in the auditory information, we get some features, we can concatenate them together. We have a matrix that has an hidden state embedding size of now 2 times the size of our original hidden state. We just concatenated them together. We've got visual and auditory features that still haven't seen each other. And then we learned some linear probe that predicts the brain data. And Model 2 is exactly the same thing, except now the vision gets to see the audio and the audio gets to see the video. So we have these contextualized video and audio features at the end of the day, which are supposed to be richer. So we did that. I'm going to play a very short video here. It's probably going to only play once and then revert to black. So this is a brain. We usually plot it as a flat map because the 3-dimensional object. So we sort of pull it apart like it's a piece of paper, and then it becomes this little flat map thing. I'll play it one more time, actually. So that's what these things in the bottom are. They're these flat maps. So there are a couple of patterns here. So on the bottom we see the visual, auditory, and synergy components of the brain signal that we can predict. So the red regions are the regions that we can predict with just the auditory modality. So we don't need any visual signal to predict these regions. And this is heavily centered on a region of the brain called auditory cortex. So unsurprisingly, this is the part of the brain that processes early sound information from your cochlea. Likewise, the green is centered mostly around a part of the brain called the visual cortex, which connects to your optic nerves. And then the more interesting thing is this last one, which is this synergy map, which primarily occupies 2 regions. One is a region called the visual ventral stream, which is believed to be responsible for higher level semantic processing after visual cortex. And the second region that is blue here is also another region called association cortex or prefrontal cortex, which is believed to be associated with higher level reasoning and thought. So the blue map is what we're training on, so just to be clear. Sorry, 1 second. Okay, so now I'm going to tell you the brain tuning algorithm. It's not a very complicated algorithm at all, but it did still take me 3 weeks to come up with, so I'm proud of it. So here we go. We first take this encoding model pipeline that I showed you before. We train the ridge rates, this beta matrix that is the linear probe that projects from our features to our parcels, and then we freeze it, and then we never touch it again. And then we just fine tune on just M, and yeah, this took me 3 weeks to come up with apparently. But so this is what we do. We just freeze the linear weights, and then we fine tune the actual model, usually with LoRa, just on the attention weights or something. So that's our pipeline. And now I'm going to present the results from doing this. So this is showing a sort of summary architectural sweep. So I brain tuned 16 Quen models for 600 steps on this brain data in this summary here. And the only thing that I varied between the parts of this model, the only thing I varied in this matrix are the parts of the model that we're allowed to fine tune on. So the y-axis here unfreezes more of the transformer layers, and the x-axis here unfreezes more of the encoder towers. So on the left, we're not allowed to train on any of the encoder towers, or on the right, you can train on both the audio and visual towers. So broadly speaking, as you go down into the right on this matrix, you get more and more parametric capacity to follow this brain tuning objective. And you can see that as you get more capacity, you can do better on this standard brain tuning task where blue is better. But of course, we don't want to just do better on brain prediction. We actually want to do better on these other downstream tasks that we might actually use our models for. So I evaluated these same 16 models, again, on 4 benchmarks. So here we have, on the top left, UCF 101, which is an action classification task. On the top right is VGG sound, which is like a audiovisual pairing task. The bottom left is MELD, which is an emotion sentiment classification task, and then ESC50, which is an audio classification task. The three matrices here use video and audio. The fourth one is just an audio task. So the main takeaway here seems to be that brain tuning the video tower is the important thing here. So whenever we brain tune the video tower, we get an improvement on video tasks. So the two columns to the right here are the ones where we did exactly that. And we see that there are broad improvements on video tasks when we do this. Audio, on the other hand, doesn't seem to get the same improvement. This is sort of the same thing we saw with the benchmarks. It might be because we have very good audio embeddings already. Not exactly sure. So the verdict is still out on whether this is possible for audio. So we did that, and those are like short architectural sweeps. So we wanted to actually train at least like one real long-term model. So this is our attempt at this. So here I fine-tuned for one full epoch over a couple of days. And then I tested on the MVEB massive video embedding benchmark. So in comparing apples to apples, so this is the Quen layer 25 embedding before and after brain tuning. And here we see actually a really nice improvement on this benchmark. So we get a 16% improvement. We improved on 22 out of 23 tasks. Yeah, it works actually pretty well. So it's great. We didn't actually have to spend a huge compute on this, and it also seems to be like a fairly data efficient method. I think it's kind of interesting that something like this is possible. I think it's kind of suggests sort of convergent evolution in the way in which biological and artificial intelligence systems actually represent concepts and abstract information. So I think that's pretty cool. I think it's a little bit of a thing to think about. But that's all I've got. So now I'm going to pass it off to Jessica for real this time, who has some very exciting work to present to you about how we can organize these complex multimodality architectures in a more natural and generalizable way. Jessica.
So just a quick recap of what David has introduced. So today's models mostly combine off-the-shelf modality-specific encoders and off-the-shelf language models. So in this setting, the encoders are not really aligned with each other. So the LM is like taking the responsibility of aligning them. So we would ask like, should the encoders be more aware of each other or just like perhaps like largely shared? So what we want to do is that we want to build an encoder which given data in any modality or multiple modalities, it can output a representation that contains enough information for any downstream tasks. So there are some challenges regarding this. So the first one is how we model the shared and private information. So for example, in speech and text, the shared information could be the linguistic context, and the private information for speech would be like the speaker, the emotion, the prosody. And for vision and text, the shared information might be the semantic content, but the private information for vision would be like the appearance, the texture, and the lighting. Another challenge would be what level of abstraction of the encoders should the encoders represent. So for speech, we have like those phonetic level representations. For text, we have like subwords. For images, we have patches. Those are like low level representations, but we can also consider doing like high level representations. And there's more. How many modalities are there? Do we consider speech, non-speech audio as two modalities, or like they should be combined to one? For video, do we think it's its own modality, or it's a combination of audio and a sequence of images? And the other challenge is like, how should different modalities interact? Like, how do we consider the modality alignment as such? So in this project, we're gonna focus on the first challenge, which is on how to model shared and private information. We kind of just made a decision for the second and third one. And since we're only focusing on uni-modality performance, we're not gonna consider the fourth challenge, and we'll leave it to future work. So here is our proposed general encoder architecture. So it's kind of like obvious from the diagram how we do like the separation of the shared information and the private information. So given a piece of data, we first pass into its modality foot. So the name foot is inspired by the name projection head, which normally represent the last layer of your model, whereas foot here would be the first several layers of your model that's tried to learn the low-level features. So after you pass it through the foot, it will be routed into two modules. One is called the general knowledge, and the other is its own modality expert. And the final output feature gonna be the concatenation of these two. So we can see that here in the general knowledge, it's gonna be the module that sees all the modalities. That's the module that learns the shared information. There are a lot of ways that you can do the training of such an encoder, and we start off with the distillation as the starting point. So here is a table of all the teachers that we use for each of the modality, the data we use, and like some architectural design in this model. So for text, we are using modern BERT large as the teacher, and correspondingly the foot gonna be the modern BERT embedding, and we train on L2 loss on fine web data, which is a clean version of Common Crawl. For image, we use Dino v3 base model, and correspondingly we use the Dino v3 patch embedding. Also trained on L2 loss on ImageNet. For audio, we use the AF Whisper from Audio Flamingo 3. And the foot is a 2-layer MLP distill from Hubert, Data to Vet, and Wavelam. And this is one of our previous work that tried to replace the CN layers of those speech models with this 2-layer MLP, and it kind of works pretty well by plugging back into the teachers and also generalized to training new speech models. And the loss we borrow from Disti-Huber, which is the combination of L1 loss and cosine similarity loss, and we use audio set for it. For speech, we use Whisper Large 3. We use the same foot as audio. We also use the same loss as Disti-Huber. For data, we have a combination of LibreSpeech, GigaSpeech, and Common Voice. So how do we do the distillation? This is a diagram of showing how to distill for one layer on one teacher per modality. So here, given an input, say a text, we'll pass through the text foot and route it to general knowledge and route it to text expert. And we concatenate the output from the general knowledge and text expert and then pass into a projection to match the teacher dimension. So we can see how this can be easily generalized to using like multiple teachers per modality, or like generalized to distill from multiple layers of a teacher. So when we do distilling from multiple layers of a teacher, we first choose, say, maybe 6, 12, 18, 24 layers from the teacher. And then we have the same mechanism, this concatenation projection, injected into like some selected layers of our model to match the different layers of the teacher. So this is exactly what we do. We just do multiple layers from the teacher, and all the parameters here shown in the model are trainable. The general knowledge and the modality encoders are all of transformer architecture. So in our experiment, we train mainly 2 models. One is a model with general knowledge having 4 layers and the expert having like 4 layers too. For the second setting, we have the general knowledge having 12 layers, whereas the expert only have like 2 layers. And for the second setting, we use like 4 times the data that we used to train the first model, and it's sort of more like a scaled experiment. So I will be talking about some of the results regarding the second setting on speech, and my teammate is gonna talk about like the evaluation on the other modalities. So here we go. This is a test result of the model where we have 12 layers of general knowledge and 2 layers of each of the modality expert tested on superb benchmark. So the first bar is our teacher model, which is Whisper Large 3. The second bar is our encoder. The third bar is an extra model that we trained that only has a general knowledge component, which is 14 layers. And the fourth bar is a model that only have the speech expert, which only see the speech data, and it's also like 14 layers. So the last 2 bars kind of serve as a comparison, and they have the same number of active parameters as our encoder. So if we compare our model to the Whisper, we can see that there is a bit of a large drop for the ASR task and a smaller drop for emotion recognition. But surprisingly, our model is doing better on speaker identification than Whisper Large 3.
if we compare the last 3 bars, we can see that our encoder kind of inherits pretty well from the speech encoder. And if we specifically look at the SID task, we can see a pretty large gap between the general knowledge and the speech encoder. And our model is, in this case, acting pretty well. So we can see there probably to some extent, there's the benefit of like separating the private information and the shared information. So this is a layer-wise analysis of our model. The x-axis is just the layer number. Layer zero is the input to the transformer block. And y-axis is the CCA score, which you can consider as a similarity. So we're testing like how each layer representation is similar to either the mail features or the phone or the word. So the darker brown one is the general knowledge layer, and the lighter color line is just the expert. And the paired circle are the concatenated features to be compared with the teacher during the training. So we can see here as the layer goes deeper, the layer representation kind of like become more dissimilar to mail features, but more similar to phone and word. But if you compare like the circles, you can see there's not much difference between the general knowledge and the expert in representing mail features or phone or word. Okay, so then I'll pass to Lin Yang to talk about the evaluation on text.
Now we do like a similar layer-wise analysis for the text branch. So the question here is that after distillation, what kinds of linguistic information are preserved in the student, and how does that change across layers? So we use a set of probing tasks ranging from like relatively shallow properties like surface, form, and morphology, and up through syntax, semantics, and the comprehension, and finally reasoning. So for all of these experiments, the encoder is frozen, and we train a separate linear probe for each task. For the teacher, we sample 5 layers across modern birds, and for the student, we evaluate every layer and separately read out the general knowledge branch, the expert branch, and their concatenation. Yeah, so here are the results, and I know it's pretty dense, and so I'll just focus on, let's say, one sub-figure. Let's look at like the tree depths, and we can find like 2 main patterns. So first is that the performance generally improves as we move to like deeper student layers, and the later layer consistence contain more linearly recoverable linguistic information than the earlier ones. That's for like the student models. And the second is that the choice of representation matters. So in general, you can see that the general knowledge branch is weaker than the expert branch. And the concatenating general branch with the expert gives the strongest student representation. So the simple key takeaway here is that deeper is better, and combining the 2 streams works best. Now let's look at a different question. Does the teacher-student gap depend on the level of linguistic abstraction? So here I group tasks by their level of linguistic abstraction. So we see a different pattern here. So at lower levels, like surface information, morphology, and the syntax, the students stay relatively close to the teacher, and in some cases even outperform the teacher. But as we move toward like sentence semantics, discourse comprehension, and those like high-level stuff like reasoning and inference, the gap between becomes larger. So distillation seems to preserve low-level linguistic information better than like high-level, more abstract information. So here we look at like the similar relationship at like the level of individual probing tasks. So the x-axis here moves from lower level surface information to higher level inference and reasoning. The y-axis is the teacher-student gap. So the values above 0 favor the teacher, and while values below 0 favor the student. So we see like there's like clear upward trend. So the surface tasks actually like favor the students, and high-level tasks more often favor the teacher. Yeah, so the main takeaway here is that the teacher-student gap tends to grow with linguistic abstraction. And so probing only tell us what kind of information can be recovered by a simple linear classifier. It doesn't necessarily tell us how useful these informations are as general purpose embeddings. So we also evaluate the same models on MTAP. So we evaluate 41 English tasks covering 7 families, including classification, clustering, retrieval, re-ranking, pair classification, and summarization. And also the encoder remains frozen throughout. And for classification, we train like logistical regression on the top of the embeddings, while the other tasks families use like the standard MTAP evaluation protocols. So here the results is somewhat different from what we see from probing. So overall, the student models much or slightly outperform the teacher on the average MTAP score. So you can see that the student performs very well in like pair comparison and semantic textual similarity. But the teacher still like performs better on some families like clustering, re-ranking, and retrieval. So the important point here is that when we compare to like probing, you can see that the loss of linearly recoverable high-level linguistic information we saw in probing does not really translate into the overall loss in the embedding performance. So I guess these two evaluations are telling us like complementary things. So probing suggests that some richer linguistic information is weakened during distillation, while MTAP shows that, okay, the compact student still like preserves, or in some cases even improves the representation structure needed for like practical embedding tasks. So next we ask whether similar depth and task-dependent trade-offs also appear in the vision branch.
Cool. Thank you, Linang. So yeah, let's try and see how the eyes of the Shonen coders actually work. As a recap, as Jessica mentioned, we're distilling multiple students, but I'm gonna try and work on 2 of these students in here. We'll look at the Dino teacher here, and we'll look at the student, which has a general knowledge layer of 4 layers deep, with an expert of 4 layers as well, and then a general knowledge tower of 12 layers, and then expert of 2 layers. We test this against 13 of the MIEB tasks, but we'll look at sort of broad family of tasks, mainly clustering and retrieval. And I've sort of left the students and teachers on the side. So how do each of these student models perform on these sets of tasks? The top 3 up here are clustering-based tasks, and the bottom 3 are retrieval tasks. And you want the main score to be high, right? The higher the score, the better. What we start seeing is actually not similar to what we saw in text, something a tiny bit different, actually quite a bit different. The teachers continuously outperform the student in every sort of task that we see, and depth really matters a lot here. When we increase the depth of the general knowledge tower here from 4 to 12, and we start seeing that in terms of clustering and these retrieval tasks, they deeper general knowledge student outperform the shallow student.
And that is the case throughout every sort of task we saw. Now we want to see, again, Chinro mentioned, we mostly take the last layer and then we move on. We want to see how each of these layers do as well. And we want to look at those two task sets that we looked at. What we start seeing is the shallow student, so the shallow student being the general knowledge layer of 4, does really well at the start, but sort of kind of rounds out, whilst we have the deeper general knowledge. It takes a bit of time to catch up, but then it just keeps on going up, as you would probably expect. We also see that the expert layer here that you sort of see is almost dead weight for these tasks, right? Like they're not really doing that well at all, as you would probably expect. Another question we want to ask, like, is there a best layer that we want to take for each of these tasks, right? And we're going to look at 3 sets of tasks here, and you'll sort of see why. So in most cases, we see that the higher layers perform better, and the student outperforms the student. The teacher outperforms the student, as you might expect. However, in some of the tasks, it's not that clear. So in some of the tasks, you'll see that some of the student is doing quite well, but then it sort of rounds out after layer 5, while the teacher keeps going up. I will kind of cheat and kind of see if the models can see what we want them to see, right? So we have your teacher and student models for 2 sort of images, and this is specifically for the 12-layer general knowledge. What we start seeing is it starts off with like patch embedding noise, and as the layers get deeper and deeper, you start seeing a bit of a structure being picked up by both the student and the teacher, right? So this is a very, very, very good sign. The task gets a bit tougher. Well, this slide's not working, but that's the perks of changing your slide in the last minute. But if this slide was working, what you would see is the color grading in here is pretty close. So the student sort of loses that sort of structure as it goes. I really want you to see the slide, so I'll fix it up later. We also want to see how the features go with depth as well for each of these tasks. And we start seeing again a similar pattern. The teacher keeps getting better or at least stays at the top for most of these tasks, and the 12-layer student sort of kind of keeps up, not really for all the tasks. Again, the 2-layer expert is again just dead weight. It doesn't really do that well. Something I didn't mention at the start is the best scores that you saw were not actually the fused weights between the expert and the general knowledge tower. It's basically just the general knowledge tower, because if you fuse it, the scores are worse, as you would probably guess. The expert doesn't do as well, right? So if you fuse that, it's not doing that as well as we thought it would. And some things that sort of show up, and here is the thing that you didn't see in the last slide, is because if the expert layer is too shallow here, it sort of loses touch with what is in the image fully and just rounds out to noise. So there's a lot of axes here, as Jessica mentioned, for training, and we want to find out what the right axes are. So what are the takeaways that we have here? The depth of the expert layers might actually play a pretty big role, right? As we see that layers getting deeper, it does quite well. Whilst if we have a 4-layer expert and 4-layer general knowledge tower, you might actually learn more coarse-grained features along the way. The extra sort of 8 layers of general knowledge start to find more fine-grained features. If you look at the bird, there it starts to sort of capture the different features of the bird that the sort of 4-layer does not capture. And in the GK two-layer expert, again, the two-layer expert does not get enough depth to learn those features that we want to do here. Okay, I will pass it on to Zihao to talk about the audio side of the.
Okay, thank you, Dan. Okay, so cool. So I would just like to understand our models, like audio understanding ability with several tasks. So what we choose is two very popular and standard tasks. First is classification with linear probing, and another is clustering. So all of our benchmarks are chosen from the, most of our benchmarks are chosen from the MAEB benchmark, and then we also add several popular sound events classification tasks to better understand of all of the scenario. So we further do some classification to our benchmarks to separate it into language related and non-language related to understand it better. So for the language related task here, they are involving people speaking, but instead of try to test the model's speech understanding ability, we are more focused on let the model to distinguish the speaker's attribute, like the speaker's gender or what the language he's speaking and his age. And for the non-language related part, there are more general audio abilities. So we are trying to let the model trying to classify about the bird species and the music types, as well as some daily life sound events. Okay, cool. So the first thing I want to the result I want to show here is the teacher versus students, their general ability. So we have two contexts of models to evaluate. I think my teammates have already introduced. So the first thing is a shallow student, which with 4 general layers for 4 layers for general knowledge and 4 layers for the expert. And another is a deep student, which we have 12 layers for general knowledge and 2 layers for the expert. And both of these models are distilled from the Audio Flamingo 3 with multi-layer distillation. And the result of all of the experiments is showing on the right. And for the student here, we choose the result for the best student. And I think the result here showing that the teacher model is outperforming most of the student model. But I think that is quite to our expectation, because our student model is much smaller than the teacher model. We are only around 10% of the parameter of the full Audio Flamingo, and we only train on a small audio subset, but we are also still having some competitive result as a teacher. So I think if we have training our student model to be longer and training with more data, I think the gap between the student and the teacher will be narrowed. And I think it's worth to point out from the results, there's some really interesting and promising results. I think that, for example, for the 2 data set, which is common language edge detection and this gender one, our student is outperforming the teacher. So these are 2 data set or benchmark that have some related to the speech. So I think when we are training doing this multimodal distillation, our audio branch is learning some general knowledge from the speech teacher, so we can outperforming these some speech tasks. And also I want to point out is that we also outperform our teacher model on the Berkeley benchmark, and this is a benchmark which is trying to separate the bird species, and I think our model is benefiting from some of the teacher or text this text teacher and image teachers, because we are trained with ImageNet. ImageNet has tons of birds in it, so we learn some birds related semantic, and which help us to surpass the teacher model with our student model. And besides this overall evaluation, we also have to do some analysis of our model. So the first thing we hear is is the expert branch versus general knowledge branch. So I think previously for vision we have seen that the general knowledge branch is always better than the student than the expert branch. But for in audio, I think we are seeing some opposite phenomenon here, that our vision expert branch is like somehow much better than the general knowledge branch, and the providing like much more like discriminative and representative audio features. And in comparison, the general knowledge somehow, because of like this kind of multitasking and multimodal distillation, their features somehow degraded. But we can also see that, but just like benefiting from this like multimodal distillation, we see some like improvement in the speech like related tasks, like the same as a common language detection, and this is clustering, the first clustering task. So it's showing some similar phenomenon as the overall evaluation. And another analysis we have done is about the model architecture. So we compare between the shallow and deep one. So I think the result, the key takeaway here is that like improving the depth of the expert is just helping more. So I think that's also aligned with what our previous slides with, where expert is contribute to most of the representation of the entire audio representation. But I think some other things may be interesting, or as trade-off here, is that when we are concatenating the expert and general knowledge like features, like if they are attributing the same, maybe same like contribution to the final representation, it will somehow like, because their distribution is a bit different, so they are featured some different, so simply concatenating them will lead to a drop in the final performance. So I think, so how to choose this like architecture is quite dependent to what's the final feature or the feature you want to use for your downstream task. And also we do some like layer-wise analysis to our audio branch. So I think audio branch is showing something quite interesting, because we find that for different layers, it is helping like different kind of like task. For the audio, for those like, the key takeaway here is that for those tasks related to really like low-level features, like maybe some like things like clustering, especially for our student models, the early layers is helping much, because it is provided with like a more like local like acoustic information. And for the later layers, it's somehow more semantic focused, and it helps more in classification tasks, and it helps in both the non-language and the language-related classification. Okay, that's the end of my part. Maybe let's pass to Sandra to do some like CKA like analysis of different modalities.
All right, thanks, Ihao. So for context, we were getting some checkpoints in the last few days and generating some of these results. So I just want to briefly mention how we're using center kernel alignment as a statistical measure to compare the similarity of feature representations, in this case of different neural network layers between experts and general knowledge models. And what I've plotted here across a few quadrants, which I'm about to show you, is first the modalities of audio, image, speech, and text. And from this initial CKA analysis, we can see that the lower layers of the expert tend to be, in general, much more similar to all the general knowledge layers with higher similarity. So in here, darker cells is showing you that, and the lighter shaded ones just means less similar. On the other hand, we observe that higher layers of the experts, so again, each one over here, are different to general knowledge layers with the wider blocks and thus less similar. From these initial results, it led us to run the same analysis over teacher representations and see what we could observe. Again, the same pattern will flow as I show each of the quadrants, and keep in mind that here I'm showing the teacher denoted on the y-axis in terms of the layers, and on the x-axis the general knowledge blocks. And so there are a few things I want to highlight. So let me just quickly show all the modalities for image, for speech, and for text. So we can definitely see that every layer is doing something different. So that's the one thing we notice. The other thing that we've tried to do here is highlight the layers that were chosen for distillation. So you see them in the white boxes for each one of them. And one of the things is that we were talking about is that we would think that the layer that was chosen for distillation would always show higher similarity when compared against the layers of the general knowledge blocks, but this is not always the case. As you can see here, this is like a very unique example where it breaks. So at this point, we're not really sure why that is happening, but as others alluded to this before, the depth of these layers as we distill from them is really important. And as I mentioned initially, we didn't get the time to do it for the 12-layer one, so that's something that we need to look into in more details. I think that's all I wanted to say for now. So I'll pass it to Jessica, who will provide us with some takeaways on training of the multimodal encoders.
So I'll do a quick wrap up. So what have we learned so far? We can see that distillation kind of to be like a valid approach to learn a multimodal encoder. And to some extent, we can also separate the general and modality-specific knowledge in our setting. And we also see a wide variation in student model performance, ranging from abysmal to better than teacher model. And we have a compiled figure in the next slide. So on the x-axis, this is our model, our student model size over the teacher model size, and on the y-axis, it is our teacher model performance over the teacher model performance, all in percentage. So the middle point is the teacher performance. So on this side, we can see in many cases, our student model is very compared to teacher model, and in some of the tasks, it's even better than the teacher model. However, there are a lot of cases, especially image, it underperforms the teacher model a lot. So this is like one of the aspects we should definitely consider to improve. So this leaves us a lot of open questions regarding the design choices that we use. So what teacher model should we actually use, and what are other training losses to consider, other data, and do we want to try to test on a multimodal data set? And we also need to do more analysis on like what our model is doing and what the teacher model is doing. So this closes our section, and we will have a 5-minute break.
Hey guys, while we're taking the break, I just want to remind people there's plenty of food, so please eat it, because if you don't, then at the end of the program, you have to throw it away. So please help yourself.
Oh, sorry, the mic is not on. That's why I had, okay, now the mic is on. Okay, this display here is turned off. There we go. Okay, perfect. All right, welcome back from the very brief break. So, so far we've talked about the unifying evaluation framework that we developed as a basically a benchmark for all the different new encoder models that we've been developing. We talked about, you just heard the multimodal encoder team talk about the efforts that we made in developing unified encoders that can handle multiple different modalities with a single model that's all trained together. And so in the third part of our talk, we're going to be talking about the design space of tokenization for continuous modalities like speech and image. Here we're going to talk about various ways that we've developed doing token compression and things like that across audio and video. So to lead us off, we're going to have Roger, and we're going to have several other people also talking about their work here, Krishna, Kiran, Sihan, and Matthew. So Roger, take it away.
Hi everyone, I'm Roger. And before we go into what we mean by multimodal tokenization or audio tokenization, let us kind of take a step back and go back to looking at multimodal language models and what we would want them to do. So a multimodal language model, you would kind of expect it to be able to process all kinds of different information in addition to text, such as videos from BBC News, for example. We would expect it to be able to process information in forms of the video frames itself or the audio waveform. For example, we would expect such a system to be able to questions about the video information itself, such as what is happening in this video, just by looking at the visual information. It should be able to give a reasonable answer, and for the audio waveform, we should be able to do something similar. If we ask the model to transcribe the audio waveform, it should also give a reasonably well transcription. Now, in the past 2 sessions, my teammates have been talking about how do we evaluate an encoder in this context, and how do we build multimodal encoders for such systems. However, in my part, I'm going to be talking a little bit deeper about the ways in which we combine a multimodal encoder or tokenizer, which I'm using the terms interchangeably here. How do we use them in conjunction with a language model? So if we kind of unabstract this diagram that I was just showing here, a typical multimodal language model is consisting of an encoder/tokenizer that processes the input data into a sequence of embeddings. We kind of concatenate them with the textual prompt, telling the model what we wanted it to do, and we ask the model to generate a reasonable response. In my part, I'm going to be focusing on this part here, which I'm trying to say, which is the embedding sequence that is the output of the multimodal tokenizers. The problem here is that existing tokenizers tend to produce very, very long sequences for modalities that are not text. For example, going back to the video example, assuming that this is a very short 5-minute video, if we took the transcription and we tokenize it with a BP tokenizer or Llama, and we take an audio waveform and process it into a sequence of embeddings using something like WaveLM, and we take the video frames and process it with a typical video encoder, the transcription would take about 960 tokens. Does anybody want to hazard a guess how much the audio waveform is going to be in terms of the length of the embedding sequence? Okay, I'm just going to show it. Yeah, it's about 15,000 tokens, which is about 16 times the amount of text tokens that were used. And for video, if we're taking, even with the most conservative estimate, where we're taking 256 times 256 images and using 1 frame per second, we will still at least get about 80,000 tokens. This is about a 16 times increase versus the text tokens and an 80 times increase versus the text tokens. So when we're processing these sequence of embeddings in a very long coding session with Claude, well, we can't really take advantage of these inputs natively. So this is also a twofold problem. First one is that the long sequences are time consuming to process. And the second aspect is that since each individual embedding only corresponds to a very small portion of the input data, then the model has to do something more complicated. It has to aggregate information across all these embeddings in order to learn something meaningful. So our research direction, the core hypothesis is that we assume we are able to compress the embedding sequence or token sequence into a shorter sequence that is both faster and easier to process by the downstream model or the language model. In essence, I'm trying to say that what I'm proposing here is adding something in the middle that tries to reduce the length of the embedding sequence produced by the tokenizer. And so the question is then, well, how do we do this? Well, there has been a lot of prior work that tries to solve this issue using something simple like, what if we just take the simplest approach and just average every fixed number of frames? So if n is equal to 2, then we can just simply take the average of every 2 frames and produce a new embedding sequence that is twice as short. Well, you lose some information, but sometimes this works reasonably well. We also wanted to motivate our next presentation presenters by a more oracle setup that is variable rate, that produces variable rate segmentations instead of a fixed rate segmentation, as I showed in the previous slide. For example, in the case where, since we're focusing on speech in our next experiments, we can take a linguistic unit such as a syllable, we can use force alignment algorithms to align it with the original speech, using the boundaries, we can obtain one single embedding by averaging all the embeddings within the same segment to produce one single embedding for each syllable, as shown in this diagram. So the advantage of this approach is that each embedding here corresponds to a variable amount of information in the input data. So if we have a long segment that doesn't correspond to much useful information, hopefully we can produce a scheme that learns to only encode this non-informative segment in one single embedding. But we're using this as an oracle setup to kind of motivate our later experiments. So I'm going to show you, me and a few presenters after me will talk about this experiments using this experimental setup, where we're training a system that uses WaveLM large as the speech tokenizer / encoder. We're going to be applying some of the compression methods here, and we're going to be using a 1 billion parameter language model as the backbone. First of all, I'm going to show you some results on ASR using the 2 compression segmentation methods that I've been talking about. So for example, if we take a look at the first line up on top, sorry, let me go into the x-axis and the y-axis first. The x-axis here is the average compression rate. So we're going to be averaging every fixed amount of frames in the baseline setup, averaging every 1 frame, every 2 frames, up to every 8 frames, or if we're taking force alignment boundaries, we can calculate the average numbers of embedding in each segment that corresponds to the linguistic unit and kind of plot it below. So the y-axis here is the word error rate for ASR on LibreSpeech Dev Clean, so lower is better in my chart here. And we have kind of 2 lines here. The first line on top is the results when we're applying the naive approach of just averaging every n frames. The dashed line here is the numbers that we get when we use different linguistic units as the force alignment targets to obtain the variable rate boundaries. So first of all, when we take a look at the fixed rate results, just doing simple averaging every n frames, we note that because n equals 1 is used doing no averaging at all here, we note that we are able to kind of get away with at least averaging every 5 frames before the error rate starts to increase. So the first takeaway I wanted to say here is that we are able to both maintain performance and be more efficient in terms of computational cost, just by doing something as simple as averaging every n frames. Okay, now that we know this, if we take a look at the forced alignment results, we note that the character level, using characters as the linguistic unit or using phones as the linguistic unit can both produce ASR systems that are significantly better than any of the systems that we have shown just here. So this is we are reducing the error rate by 50%. And the numbers here are significantly better. The fact, this suggests that we should be able to produce a variable rate scheme that can improve the performance on ASR and a whole bunch of different tasks a lot more. So Krishna will be talking about the same experimental setup on more paralinguistic speech tasks.
Yeah, so we kind of wanted to explore how the same pattern of pooling and compressing these audio tokens extends to other speech and paralinguistic tasks where there might be different audio requirements. And so the 2 tasks that we chose to consider here are stress word detection, where we basically provide the model with an audio sequence and the corresponding transcript, and we expect the model to identify the words that it thinks are being most emphasized or stressed in that particular utterance. And the second task we chose here is speaker counting, where we provide the model with an utterance that contains multiple concurrent speakers, and we expect the model to identify how many speakers were in that utterance. And our expectation here is that based on the task, we'll be able to get away with higher and higher levels of pooling based on the requirements of that particular task. And so intuition would say that ASR can probably get away with like a subword level of compression and probably no further. And we can push that with stress word detection, where we can get away with word or multi-word level pooling. And speaker counting would probably be able to get away with utterance level pooling and still not see a massive degradation in our accuracy, and that is what I hope to show. So more specifics on the stress word detection pipeline. The setup looks very similar to what Roger showed earlier. We take the audio and we pass it through WaveLM to get the embeddings, and that then gets compressed using fixed boundaries or oracle boundaries based on the setup. And that gets prepended to the LLM prompt here, which is given the audio and the audio transcript, find the words that were stressed in the audio, and I provided the transcript. And I expect the model to generate a comma-separated sequence of words that it thinks that are being stressed or emphasized. And the speaker counting pipeline, again, is very similar. The only difference here is that the prompt is different. It's now asking identify the number of speakers in that particular audio clip. And I expect the model to generate just a single integer representing how many speakers it thinks there were in that particular utterance. So getting into some results here for stress word detection, I'd like to draw your attention to a couple of things. The first is that looking at compression levels 1 through about 7, we notice that there is not much of a difference in the stress evaluation accuracy, where again, higher is better. So we notice that it hovers around 77 or 77.5%. And looking at the ranges from 16 through 64, we can see a massive and very noticeable degradation in that stress evaluation accuracy, suggesting that there is like an island of stability where we can retain much of our performance and get away with very high levels of token compression. And the red dots you see here, they're the oracle line boundaries from Montreal Forced Aligner. And you can see that the phone boundaries seem to degrade the performance, and the word boundaries seem to retain much of that performance. So unlike ASR, we do not see a distinct advantage of using the oracle boundaries, but we do still see an advantage of using token compression in general. And just to kind of emphasize this idea a little bit further, you can see that running this same experiment across multiple seeds, we can again identify this island of stability where, despite there being a little bit of a high variance, we can retain much of our performance before it starts falling off quite drastically once we get past a compression level of about 8. And so one question I want to quickly pose here that we were kind of discussing when we were working on the stress detection results is, why are we mean pooling? And why don't we use some more learned approaches like an LSTM? And so we ran some evaluations on this using an LSTM and an LSTM bidirectionally to kind of see if we can learn the pooling on top of the boundaries to be a little bit better and improve our performance slightly. And what we're noticing here is that although there is a slight advantage the LSTM poses in some cases over mean pooling, this pattern is by no means consistent. And the differences we see aren't even that massive. And this is likely for a couple of reasons. One of the reasons is that the LSTM is being cold started when the rest of the training setup is using LoRa, which is obviously warm. And so catching up to the quality of the embeddings that WaveLM naturally produces may be difficult. And additionally, mean pooling might be one of the things that WaveLM naturally supports, having very high quality embeddings, and the mean operation might naturally fall within the semantics of those embeddings. And so moving on to some results for speaker counting, we can see the same concept of this island of stability that we saw with stress detection, but broadened to a much higher level of compression. And so you can see here that we can retain roughly 60% speaker counting accuracy while pushing the compression all the way to about 32. And this suggests that based on the task, we can get away with higher or lower levels of compression. And this is really dependent on the task itself. And I think this idea is even more emphasized when you look at that purple line going across. And this is the CLS baseline where we pulled all the audio tokens together, and we can still retain a lot of that performance, seeing only about a 5 to 6% degradation. And this again really suggests that pooling and compression is task dependent, and we can get away with much higher levels of compression on certain tasks. And so, as I said, the kind of key takeaway here is that compression is task dependent. And in many cases, a variable rate compression scheme like the Oracle you saw with the ASR results can improve results even further. And next, I would like to introduce Karen to kind of talk about how we connected speech tokenization and compression with the tokenization of the LLM models that are being used downstream. And further, our teammates will kind of describe how we learned a variable rate compression scheme. So.
Great. So far, you've heard Roger and Krishna talk about what happens when we change the size of the speech tokens or the speech segments that we combine into tokens that we feed to the LLM. So now we're going to talk about the interplay between the speech tokens and the text tokens in the text language models that we're combining them with. So we're going to consider the LLM tokenizer of our backbone. So this is the type of model that Roger and Krishna have been using. And now we're going to ask the question, is the tokenizer, which is a BPE style tokenizer in that pre-trained language model, the best fit for other modalities? So we've seen that different size speech tokens might have performance or efficiency benefits. And the best speech tokens might be more like phones or syllables or words or some other natural speech unit. But BPE style tokenization doesn't naturally align well with any of these. So let's consider some other text tokenizations and see what happens. So what are some alternative text tokenizations? So let's consider a random English sentence drawn from the distribution of English, totally not cherry-picked. For example, this sentence. And let's consider a few different ways of tokenizing that sentence. So one is the traditional BPE style tokenization. I won't move because the mic is here. But I wanted to point out that if you look, I can. Okay, fine. So you'll notice that some of the BPE tokens are whole words, some of them are syllables, some of them are random sequences of characters, some of them are single characters, and this is naturally not going to align very well with any one type of speech token. On the other hand, we can consider word tokenization, where here every single token is a whole word, and of course that aligns nicely with speech, but there's a reason that we've all been using subwords, which is that words don't have perfect coverage of any text corpus. We can think about syllables, where we break up words into more natural subword tokens, natural speech-wise. So for example, Sanjeev now gets broken into San and Jeev, and Paula gets broken into Pau and La, which both should align better with spoken segments. And then we can also do character tokenization, where we just consider every single character to be its own token. Okay, so we trained a bunch of different language models using these different tokenizations. We trained language models from scratch. And so to make it all fit into the span of our 6-week workshop, we trained fairly small models. So the results that you see from now on tasks are going to be on a different scale from the ones that you saw with more powerful language models before. So we trained models with the GPT-2 small architecture, 124 million parameters, trained them all on Wikitext 103. We trained a model with the original BPE tokenizer, which is 5,000 BPE tokens, 50,000 BPE tokens. A word-based model, which is also 50,000 tokens, where we reserve 2,000 tokens as a BPE backoff, so we don't have any unknown tokens. Same thing with a syllable-based model, 50,000 tokens, 2,000 of them are BPE backoff, and a character-based language model, which is 512 character tokens. The syllable-based language model proved to be the hardest one to build because notice that what we need here is a text syllabifier. Phonetic syllabifiers are fairly easy to come by. Text syllabifiers don't actually work that well out of the box, at least not the ones that we found. So if you take an more or less off the shelf, we had to build it by combining a couple of components. But a more or less off the shelf basic text syllabifier will take a word like tokenizer and produce 3 syllables. How many syllables does tokenizer have? 4, good. Okay, so that was no good. So what we ended up doing was taking our text, converting it with a G to P model to phonetic sequences, tokenizing the phonetic sequence, which is a lot easier, and there are great models that can be used off the shelf, and then realigning that back to the text. So we end up with a better text tokenization. So as a byproduct, we have this text syllabifier in case anybody here needs it. Okay, so how do our language models do on traditional language modeling metrics? So we look at the perplexity per word of each of our models versus the size of our token, so the number of characters per token. What we see here is that the syllable BPE and word models are fairly similar in terms of perplexity per word, around 30 or a little bit in the low 30s, whereas the character-based model, as you might expect, has much poorer perplexity. But this is not our goal. Our goal is not to improve perplexity. It's to better match speech tokens. So next, Roger and Krishna will take each of these models and apply them to our speech tasks.
Yeah, so as Karen just mentioned, one thing to keep in mind when we're going to look at the results next is that most of these language models have similar perplexity, so maybe they should have similar performance. In particular, the character model actually has worse perplexity, so it should be worse. However, when we look at the results when we're using these language models in a speech LLM system and we train them for ASR, we note that the best result here is actually with a syllable language model and a character language model. And they are both significantly better than what we would consider to be the baseline, which is using a BPE language model and using something very simple like averaging every 5 frames here. So the interesting here to note is that we are able to get significantly better performance than a BPE model baseline on ASR if we use something that more correlates better with speech, such as a syllable language model.
Yeah, and I want to kind of extend this pattern to the stress detection results, where again, you can see that, in fact, the best performance that we got was through a character language model with the CTC word boundaries. And the worst performance we got was actually going to be the baseline here, which is BPE and a fixed rate. So this kind of suggests this idea that we need to be looking at both axes, that the axis of the oracle segmentation, as well as the tokenization of the LLM itself, and we have to consider those jointly to see how different tasks behave. And the other thing I would like to point out here, and this is kind of similar to the results from ASR as well, is that it is not necessarily true that matching the language model with the corresponding segmentation gives us the best results. In my case, it was true with the character and CTC, but it is not the case for the rest of the language models like syllable and word, and the same applies to ASR. So that is one more interesting find that I'd like to point out.
Yeah, so kind of as a small wrap up to this section, the interesting thing is that even when the language models we use have similar perplexities per word, the text tokenization that they are trained on actually still significantly affects their performance when we use them in a speech system. And the second thing we'd like to point out is that the default pairing that we use right now, a BPE language model with something very simple for the speech embedding sequence, is pretty suboptimal. In both ASR and stress detection, we were able to get significantly better pairings for both tasks. So the question next up is, well, how do we find these pairings? But we didn't have time to look at that. And next up, Sihan is going to talk about the question of, we already showed that there should exist a variable rate tokenization scheme that improves downstream task performance. But can we learn this using reinforcement learning?
All right, thanks, Roger. So the project I've been working on focuses on this, learning this adaptive tokenization for speech using reinforcement learning. So as Roger mentioned earlier, it's nice to have this oracle boundary rate downsampling, which looks pretty promising. However, in practice, the issue is that we can't really have those alignment-based segmentations before we actually do ASR. So the method we're proposing to handle this is to learn a adaptive segmentation via a lightweight segmenter, and we learn it through reinforcement learning. So the tasks that we're focusing on for this prototype is ASR, and the data we're using is slipper speech 100. So this is how we're modeling the whole thing. So we start with when we have this waveform inputs, we pass that to a regular speech encoder. In this case, we're using Wave2Vec2. Gives us a set of features at a frequency of roughly 50 hertz, exactly 50 hertz. And then we pass that to the segmenter, which gives us a one binary logit per frame. We pass that to the like main pooling operation, which then averages the binary embeddings. So more specifically, the segmenter will produce a bunch of zeros and ones. One indicates the segmenter thinks it's a good binary, and all zero labeled frames will just be main pooled with the first binary frame to their left. And then the downsampled representations will be just projected and passed to the decoder to generate the ASR transcript. So the main challenge with this setup is that is differentiability, right? So specifically, this operation of first sampling segmentation followed by main pooling makes the training a bit tricky. So there may be more than one way to work this around, but the approach I explored was through RL. Matthew, who will be presenting later, has a different approach that doesn't explicitly involve RL, but I will first go through this stuff that we're working on. And just a little spoiler alert, we'll be seeing the first equation of today, so don't fall asleep yet, I promise it's gonna be quick. Okay, so GRPO. The specific RL algorithm we're using, I'm going to very quickly walk you through how this works in our setup. So we have this waveform, we pass it to the segmenter, we pass it to the encoder and then to the segmenter. So the segmenter, or in the RL language, the policy model is basically a set of convolutional layers with approximately 1.6 million parameters, which is also nothing compared to those billion level parameter LLMs. So the segmenter will generate frame level binary logits. After we obtain the binary logits, we do a Bernoulli sampling, which gives us, in this case, 4 sampled segmentations, which will then be passed to the decoder, who will eventually generate speech logits for computing the, transcript logits for computing the rewards. So the key supervision signal of GRPO comes from this grouped advantage term. But in its essence, it's really just a bunch of scores or rewards. Here we use teacher first log likelihood as our reward function. Basically, it's just aggregated token level cross entropy. And here's something that's not part of the original GRPO algorithm, but crucial for our setup. Specifically, we introduced this term of downsampling ratio regularizer. For each sampled segmentation, we compute the downsampling ratio, or essentially the number of ones. And then we penalize the policy model if the ratio goes out of the range that we specify, say in this case, from 0.1 to 0.3. So the upper bound here is to prevent the segmenter from just lazily generating all ones, and the lower bound is to prevent it from collapsing and generating all zeros. So, so far the RL setup sounds great, but in reality, it is also known for its instability. So in our case, we found that the training very quickly collapses without a proper initialization, partly because of the very large negative log likelihood is not providing much useful optimization signal. So as this plot is showing, the x-axis here is the number of epochs that were trained, and the y-axis here is the token cap ratio. So the red line here is an experiment we conducted for which we do very little like warm up before we start RL training, and the gray vertical bar here indicates the step that the RL starts. So we see that this segmenter collapses really quickly after the first epoch of RL training, and it generates only zeros. So to stabilize things, the fix we tried was curricular training. So in stage 1, we co-start the segmentation model, training only the segmenter on this CTC aligned character level targets using the BCE loss. And then in the stage 2, we warm up the decoder to give it at least some very basic ASR capability. In this stage, we only train the projector and the decoder via the regular ASR cross entropy loss. And finally, in stage 3, we grab the co-started modules and update them jointly through these 2 branch gradients. More specifically, the segmenter or the policy model only receives gradient updates from the GRPO laws, where the decoder just gets its updates from the supervised token level cross entropy laws. So, oh, did I hear a question? Okay, sorry. As we see, the resulting model is this green curve in the plot, which apparently has a much more stable training dynamics. And here are some of our preliminary results. Since this is a prototype, we're training only on the 100-hour subset of labor speech. So the numbers may not be directly comparable with some like other numbers we see from other slides. The x-axis here is the token cap ratio again. The y-axis here is the word array. So ideally, we'll have some like a more bottom left point suggests that the model can do better ASR while consuming a lower frame rate input. So we see that the gray line here represents the baseline we're comparing against, which are those fixed unsampling rate models. And the light blue bar here is the version of the model which doesn't train the decoder at the final stage. And the darker blue bar here is the setup for which we jointly train both the segmenter and the decoder in the last stage. So basically the takeaway is that the jointly trained model is we're doing better in terms of ASR while consuming fewer speech tokens comparing to the other models. And here we have a like qualitative example, randomly sampled from the validation set. So the first row is the spectrogram of this occurrence of the speaker saying a shop girl was the destiny prefigured for the newcomer. The second row here with all the blue bars are boundaries generated through these CDC alignment boundaries. And the third row here, the red bars are showing the model's segmentation policy after we jointly train the segmenter and the decoder. So we see that the red boundaries here are more sparse, meaning the compression rate increased a little bit. And we see, like, if you can see the characters, there's a small pattern. So T and H is getting merged. So does S and H. So it's learning some sort of phoneme level segmentation, I guess. So the takeaway, so the RL looks promising, it's helping us. And the policy gradient optimization looks effective. And we'll be extending it to more settings. But there are also other ways of solving the problem. So with that,
yeah, I have a very quick clarification. Go back to any one of your slides with the ratio on the x-axis. Yeah, this one's good. So I'm trying to map this. So syllable level would be, I'm thinking 0.25, because if you're looking at 50-second frames, 50 millisecond frames, syllable about 200 milliseconds. So 4 to 1 would be a syllable, and maybe 0.1 or something is phoneme, or how should I, basically I'm trying to having a hard time mapping what people were talking about earlier with this row.
Yeah. I think your estimate was fairly close.
Yeah.
I don't remember the number exactly off the top of my head. Oh.
Okay, so 0.2 would be syllable. Yeah. By the way, use the mic. Yeah. Yeah. So anyway, David just said the syllables are about 0.2.
Yes. So to contextualize this against all the stuff that Roger and Krishna and Karen talked about with respect to, phone, syllable, and word. So phone compression would be somewhere around like 0.33, right? Because it's usually around a compression ratio of like 3 frames per phone or character. Syllabic tokenization would give you a compression ratio about equal to 5 to 1, so that's the 0.2. And then word level would actually be all the way down here. It was like a 12 to 1 or 13x compression ratio.
Yep. Thanks. So yeah. So with that, I'm passing to Matthew, who will be presenting a different approach of generating the segmentation policies without involving RL.
Thank you. So as Sihan mentioned, I'm going to talk about some other ways that we can learn this tokenization. So you can think about it as something you could use in the same context Sihan was. However, in this case, I focused mostly on validating some components we had to build for it in an encoder-only setting. So just to motivate this again, we have some encoder, maybe attached segmenter, and what I'm really focusing on here is we would like explicit control of the frame rate out. So if you look at this very AI-generated picture, you can see that in some cases I'd like to, basically, I'm cheap, I don't want to use too many tokens, and it would be great if I could just produce few tokens out so that my LLM works better. There's some existing methods that do this segmentation, like learned segmentation, but in general, it's very hard to explicitly control the rate. There's some threshold that you have to tune, and it depends on the task and the data, et cetera. So let's just directly control the rate. So here there's no RL. We can use a straight-through estimator. You can even do it in a soft way without the straight-through estimator, but I'll talk about the straight-through estimator way. Oh, the end goal of this is that ultimately, if you know that certain tasks require much less compression, you can get away with compressing the audio much more. Maybe the prompt basically just encodes from the start what the desired frame rate should be or could be, and you could end up learning that. That's future work. We're not talking about it here. This is more about validating components, okay? So I would interpret all the results I show you in terms of validating the components we built for this. So what are these components? Well, I have to tell you about this variable rate resampler with the straight-through estimator as opposed to RL. Now, we had a very nice talk by Ramani earlier on here who told us about the importance of rote embeddings. These are like rope embeddings, but you basically use time instead of position. So I thought maybe that's something we should investigate. Then the other thing that was concerning to me was all of our loss functions that we're using to pre-train our encoders, they don't know natively about time. So if you have, for instance, a variable rate segmentation, but also different inputs such as video, audio, et cetera, they might have packet loss. You might have decided to remove some frames because there wasn't anything interesting going on there. You know, you'll need to have some notion of time encoded in the loss function, you would think, in order for it to learn good representations. So I'll tell you about these components. So first, the variable rate downsampler. There are many ways of doing this. This looks quite similar to an approach called continuous integrate and fire, but here you have explicit rate control. So you have dense representations. This could be input features or some hidden representation in some transformer. And you need to create some density over which you're going to sample them. One easy way to do it is you can measure local change and turn that into a distribution. So it's basically what's the fraction of change that I've observed over time at any given moment. So once you have this distribution, you can normalize it and turn it into a CDF. And if I want explicit rate control, what I'd say is, well, I need 5 or 10 samples out of this. So let me place equally spaced quantiles in my CDF. I can see where those points intersect my CDF, and those are places that I should probably sample. So basically, steep parts on the CDF, there's a lot of change, and so you should probably sample from there. So you're asking the question, where in time does 50% of the change occur? It could be very early or very late. All right, once you have that, those become the segment boundaries, and you can come up with different ways of pooling them together. Okay, we tried a very simple thing for now. All right. So how do you encode time? So I mentioned rote embeddings just as sort of a straw man other version of doing this. What if we just use the positional encodings, but we just keep track of them after the downsampling and always map back to the original grid? So we always have a reference in time that we can point to, and you just evaluate all the sinusoidal positional encodings at the original grid. So just a comparison point. We can also compare to just not using any embeddings at all, because maybe actually it doesn't turn out to be as important as maybe it indicated. All right, and then the time over loss functions. So to motivate this, just consider CTC as a starting point. We've talked about it for alignment. You can use it in some cases for SSL pre-training. It's not natively aware of the frame duration. So since we're slicing and dicing the signal in sort of arbitrary ways, let's just think about using continuous time as the basis for this, because now if I can get it to work there, I can chop up the signal however I want and everything will work. So there's a continuous time formulation of this. So what does this look like? Well, in CTC, if you interpret it in one particular way, there are sort of different flavors of CTC. There's one called HAT that I like a lot that kind of factorizes the blank token from the other predictions. You can think about the blank token, the probability of producing blank, as basically the probability of not doing anything new. I'm going to wait where I currently am, and then at some point I'll change. Okay, and so that change part ends up being 1 minus the probability of waiting and then producing the thing that you're supposed to produce. Thing is if you take this into continuous time, the limit of this geometric series, you end up with like a Poisson process, like waiting time process, and the waiting time is modeled as an exponential distribution. So this is the CDF of the exponential distribution. And what you see is that really the probability of blank is encoding 2 things. One, the rate of where you currently are, and then also the duration of the segment that you're currently in. It's modeling them jointly, and if you have a fixed frame, fixed uniform grid, well, that's fine. It doesn't really matter because delta t is always the same. But now if you have variable length segments, maybe it matters. So we can think about looking at just the rate and modeling that. Okay, so now that we're in continuous time, just so that you can see how this sort of works. So in normal CTC, you have discrete steps, and it all works by the forward algorithm, which roughly looks like this matrix multiplication you see on the left. It lets you recursively compute the marginal probability over next states at the next step. In continuous time, this transition matrix sort of turns into a rate matrix, is what it's called. That's this thing Q, and this is telling you what the change is at any given moment in time. So to transform this continuous time formulation into something we can work with, we need to solve an ODE and ultimately discretize it. One way you can do that is assume that that Q matrix is piecewise continuous over time. And when you do that, you can actually solve for the transition matrix P. And the interesting thing that we see there is that now P, the transition matrix, actually depends on delta t. So the transition depends on the duration of the segment. And that was what we wanted. So now we just have to come up with a neural network that can parameterize this matrix and depending on the delta t. All right, so we're going to train a bunch of encoders. Remember, the idea is that we want to have one encoder that can give us somewhat stable performance across as many rates as we want so that we can decide to control the rate and get a similar performance out. So we'd expect flat performance for as long as possible, and then at some point you compress too much in time and you start losing performance. So we'll compare CTMC versus CTC, different embeddings of time, and rate control. We also looked at some other parameterizations of the rate matrix. So one nice thing about this formulation is it actually, I don't know how relevant it is to our overall goal, but a nice happy accident is it unifies a lot of different objective functions. So it turns out you can formulate the RNNT objective, a lot of these different CTC objectives, and this one, all in the same framework. So all you have to do is parameterize this matrix Q differently, and that's just on the neural network level. There's one single loss function. All right, so first let's just check that this segmenter does something that looks somewhat reasonable. So here is an example spectrogram. At the top, you'll see when we have no segmentation, so this is the native frame rate that we would get without any extra downsampling, and then you can start downsampling more, 12.5 hertz, 6.125, 3 hertz, etc. The main thing, it's hard to know what a good segmentation would look like for any specific task. I think the only thing we can say confidently is silence probably doesn't need too many samples. So that's all I really am looking at here. And also maybe long, stable regions of vowels don't need too many samples. And if you look, those are exactly the places where the segments are dropped. So, okay, this is sort of first step validation of our variable rate downsampler. All right, so how about these time embeddings? So we looked at different embeddings of time. We also looked at explicitly embedding the rate that we're targeting, because maybe the network might learn to encode things differently if we request a different rate. It turns out that none of it really matters. So no positional encoding worked as well as the rote encodings. The physical center sinusoid thing that I described doesn't seem to work quite as well as the others. So we use the rote ones just for the rest of the experiments, but it's not totally clear from these experiments, at least, that this time embedding matters, at least for the ASR task, but these are somewhat preliminary, so I wouldn't read too much into these. All right. Now, what about the two objective functions, CTC versus CTMC? So this plot is indicative of many plots I've generated looking at these. the result is always the same. The CTMC objective is always slightly better. So I think there is some improvement that we get from modeling the duration. It seems to be a little bit smaller than I would have hoped for, but I would also say these are preliminary, and I guess we'll see how things shake out in the end. But I'm somewhat encouraged by this, at least. And just to show you that we can parameterize things in interesting ways, this is the exact same loss function where we've just come up with different parameterizations of this Q rate matrix, and we can get something that looks exactly like CTC. We can get something that looks like RNNT, which is on the bottom, and that gives us quite a lot of improvement. And okay, the other thing I'd have you notice on this plot, so on the x-axis is the output rate. It's very flat across time, and we start seeing degradation at maybe 10, 7.5 hertz, somewhere around there. So we've constructed an encoder that at least behaves the way we wanted. So some conclusions. I think the main thing is right now we have some new artifacts. There's a new variable rate segmenter that you can kind of use as a plug-in component. There's a new continuous time formulation of CTC, but also I mentioned some other loss functions based on this CTMC formulation. Maybe CTMC improves performance. I think we need more tests, but right now the results are somewhat encouraging. The improvement was better at lower rates, so when we were compressing more. And so I think that sort of wraps up our section. Roger is going to sort of give you a broader conclusion now of everything that we've done here. Thanks.
Yeah, thank you, Matthew. So kind of as a takeaway of our varying attempts in this direction of trying to compress the embedding sequence of the output of the speech encoder, more broadly speaking, my results and Krishna's results kind of suggest that we can get away with some averaging or some compression that makes the system faster and makes the performance either comparable or even slightly better. And the second thing I wanted to emphasize is that depending on the task, the amount of compression you can get away with is dependent on the task, of course. So for ASR, it's about 5 or 6. For stressed word detection, it was about 7 or 8. And for speaker counting, it was much larger. It was around 16 or so. And after our results, we kind of had 3 orthogonal directions that we attempted. One was Kearns experiments, where we kind of also thought about adjusting the text tokenization of the language model and how that interacts with the token level, with the granularity of the speech compression. And we showed that we can significantly improve results if we adjust both the text tokenization and the speech tokenization here. And Zihan and Matthew talked about 2 different ways we can kind of learn this variable rate segmentation. Zihan's direction was kind of applying this after the encoder, while Matthew tries to do this directly in the encoder itself. And we have our preliminary results that kind of suggest, okay, maybe both of these directions are promising. So that's about it for our direction. And last but not least, our team lead, David, will be talking about all of our results so far have been looking at a multimodal LLM with an encoder that plugs into a language model. There have been some recent works that say, well, what if we just use something like Mel's filter banks and image patches and just dump it into a language model and just train it? What does that work? So David will be talking about some analysis.
Okay, thank you, Roger. So I'll take just a few minutes to talk about some of the things that I've been working on, and then I'll stay up here and I'll do the team wrap up for our whole presentation. Okay, so what I'm going to be talking about to you today is these recent encoder-free LLMs. So actually, during the workshop, or slightly before the workshop, there were a couple of models that were released. One was from Thinking Machines. It's called the Inkling model. It's really, really big. I don't even know how many tens of billions of parameters. It's huge. We weren't able to work with it. But Google released the Gemma 412B model right around the start of our workshop. And the idea with this model is that it's so-called encoder-free. And so all of the models that we've been looking at today, they've got these encoder modules which will process an acoustic waveform or a video or an image. And these encoders usually have on the order of hundreds of millions, and sometimes even billions of parameters within themselves, right? So they'll take a waveform and they'll encode it in some sequence of tokens that capture the abstractions that we care about, right? So speaker identity, word identity, phone identity, emotion, things like that for speech, or maybe object and texture and things like that for vision. But these encoder-free models, what they do is they say, we're going to just not use any of that. We're just going to take those 16 by 16 or 8 by 8 pixel patches that you would apply to an image, or we'll take just a sliding window of samples, raw audio samples from the waveform. We're not even going to do a Fourier transform or anything like that on it. We're just going to take those, treat them as a vector, and then project that into token space and hope that the LLM can just handle all of this, all these multimodal tasks without any kind of more abstract encoding. So there is going to be a lightweight encoder here for each modality, but it's basically going to be that linear projection, that connector layer, which is going to take a vector of 640 PCM samples and project it into whatever the dimensionality of the token space of the LLM is. And then in theory, you can just train this whole thing with next token prediction across a whole wide range of tasks, which would encourage the model to learn the right kinds of encoding abstractions. Okay, so what we were asking here is, well, are these encoder-free models actually encoder-free, right? It's well established in the vision community and the speech and audio communities that these really powerful encoder models that we learn with self-supervised training or sometimes supervised learning, they dramatically reduce the sample complexity of a really wide range of downstream tasks, right? You can do this label-free pre-training, and you get a pre-trained model, which you can then apply to whatever you want: action recognition, image classification, speaker identification, ASR, emotion recognition. And you only need a really, really small amount of supervised labeled training data in order to get really, really good performance, right? Much better than you would get if you just tried to train that same model from scratch on your small amount of data. So we know that these encoders are really, really powerful, and these are often the same encoders that we're using as the tokenizers, or as the basis of our tokenizers for these multimodal LLMs. So our hypothesis is that, well, maybe these encoder-free multimodal LLMs are just rediscovering image and audio encoders within their early layers. Maybe if you take a shovel and you start trying to dig through the layers, you're actually just going to discover, oh, there's an audio encoder living inside this, or there's a video encoder living inside this. So that's the hypothesis that we're going with here. So we did a couple of experiments to sort of test this hypothesis and see if we could find evidence for or against it. So the first experiment that we did is looking at the context invariance of the embeddings that were derived with the Gemma model. So the hypothesis here is that if Gemma 412b is implicitly learning these modality-specific encoders, maybe within the first few layers there's an audio encoder and an image encoder, then there should exist some layer L such that the representations of an input, let's say audio waveform, which you could repeat this all with text or with images, but let's just say for the sake of example, an audio waveform, up to layer L, the representations that I would get at the frame level, right, or the token level for the audio input are going to be invariant to the changes in the surrounding context. So in other words, if I'm encoding the same waveform and I mix it and match it with different images or different pieces of text, which may be relevant, may not be relevant, the LLM is basically just going to cover its ears and ignore, well, I guess maybe in this case not cover its ears, but cover its eyes. And it's going to ignore all of the other inputs and say, you know what, I don't care what's around me. I'm encoding this audio waveform the exact same way, regardless of the context, up until layer L, right? That's the idea. And so what we did here is we said, let's take 1,000 LibreSpeech utterances. We're going to encode them in a completely neutral context. So I generated this gradient image that you see down here, as well as we just took some, neutral text like lorem ipsum, et cetera. And then you can just encode the waveform in the context of these completely neutral inputs. We're going to extract frame level representations of each audio waveform from a series of layers throughout the model. So there's going to be these yellow dots over here. And then what we're going to do is we're going to take other images and other text prompts and re-encode the same audio. So I could take text, which would maybe be task specific, like say, transcribe the words in the speech, or recognize the emotion in the speech. Or I could even just give a text transcript of the exact speech that I gave to the model, right? Or I could give the model an image of a dog if somebody is talking about they just got a new dog. Or I could, give a real image which is not matched, right? So I could give a picture of a tree or something if somebody's talking about their dog. So I can perturb the encoding all these different ways, vary the context. And then for each one of those perturbations, I'll just extract these yellow frame level representations for each layer. And then finally, what we're going to do is we're going to measure the embedding similarity of these different contextually encoded audio waveforms against the neutral anchor. We're going to use centered kernel alignment to do that because it's robust and invariant to things like rotation and mean centering and stuff like that. Okay, so the results here are that varying the context results in little to no drop in the CKA similarity of the different ways that you could encode the audio measured against the reference for about the first 12 layers of the model. And then we start to see a drop off, and really at layer 20 is where we see this very steep drop off where if you change the context, the audio gets encoded completely differently. So it seems like the model is doing heavy contextualization eventually, but early on in the first 12 or so layers, the model basically says, I'm going to encode audio the same way no matter what is around me. We can repeat this experiment, but instead looking at images instead of audio. So here what we did is we took 797 MS COCO images with their paired captions that describe the image. And then we could mismatch those. So I can take an image of a dog with a caption, you know, a furry dog catching a frisbee or something, and then I can mismatch that with a completely different caption of, you know, a person riding a motorcycle. And then I'll encode those things together. And so we want to see, okay, what is the similarity between the image representations when we encode them with matched or mismatched captions? We don't look at audio here for sort of kind of intricate reasons. Gemma uses causal attention. It has a specific token layout. So actually audio comes after images and images can't attend to audio no matter what. So we're only looking at text and images here. But we actually see almost the exact same pattern, which is whether or not you match the text with the image tokens get encoded about the same way up until layer 15 or so. And then we start to see the similarity drop off much in the same way that we saw with audio in the previous example here. Okay, the next analysis that we did is a causal intervention analysis using an evaluation data set that's meant for multimodal inputs. So OmniBench is a vision plus audio QA data set. Right? Everybody's familiar with audio QA, AQA, and video or visual question answering VQA. OmniBench tries to put those together, and it's got about 1,000 questions where they're constructed in such a way that in theory you should need both access to the image and the sound in order to correctly answer the question, okay? So what we're gonna do here is we're gonna say, all right, for each test example, we've got the waveform A, the text prompt, the question T, and then the image I. So there's two different ways that we can imagine doing evaluation on this data set. I can do it just the normal way that you would expect. I concatenate these inputs, the audio, the text, the image, and then I feed them through the respective, you know, tokenizers, really just like single layer projections, and give them to Gemma and have it answer the question. So that's option one here. The second thing that I can do is I can completely separately encode the audio, the text question, and the image with 3 completely independent forward passes through the model. And I can add a hook to the model that extracts the representations at, let's say, layer L-1. Then after I've done a forward pass 3 times through those L-1 layers, I will concatenate their embeddings back together, feed them through the remaining layers of the model, starting at layer L, and then answer the question. So what this is going to tell us is if text, images, and audio are all processed independently up until layer L, then we should see little to no difference in the performance of the model on this question answering task, right? And then eventually, once the model actually starts to do contextualized encoding at some layer, we should start to see the performance drop, okay? And remember, we saw layer 12 is where the similarity starts to drop with CKA for audio, 15 for images. So where do we think the performance is going to start to drop for OmniBench? 12. Okay, it's actually, it starts to dip around 12, maybe 14. It starts to become statistically significant around layers 16, 17, and 18. So the dashed line here is that baseline. It's what you would get if you followed procedure 1, where you encode everything jointly, and then doing the kind of slice and dice and remerge at layer L, where L is shown on the x-axis here, is going to be the red line. So wherever we see the red line start to dip statistically significantly underneath the blue dashed line is where we can hypothesize that this causal intervention is kind of revealing where the contextualization is happening. So yet again, another piece of evidence that seems to point to kind of layers 12 through 15 is where contextualization starts to happen. Okay, we can do another experiment here where we can actually look at what do we think these first 12-ish layers are actually learning. Are they actually encoding things that we can interpret? So we're going to follow some very well-known work from Karen's student Ankita Prasad from a few years back, where she wrote a series of papers looking at the layer-wise analysis of self-supervised speech models, trying to see which layers specialize in uncovering acoustic information versus phonetic information versus lexical information versus semantic information. And a lot of these really well-known models like Hubert, Wave2Vec2, they kind of follow a very nice intuitive progression where they first kind of the first few layers look at acoustics, and then you start to seeing phonetic information, and then words are composed of phones, and so the layers after that start to learn word level information, and then that information becomes more semantic, etc. So we wanted to see if a similar trend exists with this Gemma 12b model. And what we saw is that there are some very striking similarities between the first 12 layers of Gemma and these self-supervised models like Hubert, Wave2Vec2, WaveLM. There's also some interesting differences, which I'll comment on. But the first thing that I want to point your attention to is that the same way that we have this kind of phonetic information peak followed by a lexical information peak in the self-supervised models, the exact same thing happens within the Gemma layers. We have a peak at layer 8 for phonetic information in Gemma, which is the red curve. The other curves are the self-supervised models. And then followed by that's followed by a peak in the lexical or the word level information at the layer right after that, at layer 9. One thing I want to point out here is that if we're looking at the similarity of the embeddings against acoustic information, so we're using the CKA against log-mel filter bank energies as the proxy for that, you see the self-supervised models start at a relatively high number. That's because we chopped off the CNN waveform encoder. So remember, all these self-supervised models have 7 layers of convolutions going over the waveforms. And so this first layer, which is the input to the transformer stack, already has learned something pretty acoustic. Whereas it seems like Gemma spends the first 3 or 4 layers basically rediscovering the log-mel filter bank feature extraction pipeline. And the reason, sorry, well, I'll get to the numbers later, but this CCA correlation that we're looking at here is incredibly high. It's like 0.96 at layer 3 with log-mel filter bank energies. We also see similar curves between Gemma 4 and the self-supervised models for both part of speech tags as well as word level meaning. Although these experiments didn't quite, the reason that we did these experiments, these first 2 on the left looking at part of speech tag information and word level semantic information, is because we started to see this steep drop off after sort of the phone and the word layers, and we started to think, okay, well, what is the model representing with these layers here? So we thought, well, maybe it's starting to learn higher level things. Let's look at part of speech. Let's look at the word level semantics. But those experiments also showed a drop off, so that wasn't the answer. So then we started to think, okay, maybe these layers are actually starting to look at whole sentence information. So we took the text transcripts of the audio, encoded them with a state-of-the-art sentence embedder, and then looked at the CKA similarity of the frame level representations with the sentence embeddings. And that's where we saw a big peak coming right after the lexical peak. So right around layer 10, we see this big jump in sentence similarity between the speech embeddings and sentence embeddings. It does kind of drop off after that, though. It still remains higher than the layers before it. So it's still kind of an open question exactly what's going on with these higher layers. But this does seem to suggest that there's like broader temporal contextualization within the acoustic waveform happening within the model layers at that point. Okay, so the takeaways of this analysis is that despite the fact that Gemma 4 12b does not use these modality-specific encoders that are explicitly separated from the rest of the model, it does appear to learn to use the first 12-ish, give or take, the transformer layers as encoders for text, image, and audio inputs. These embeddings, I didn't show all of the analyses that we did here, but we did some other experiments that showed that within these first 12 layers, images, text, and audio kind of occupy orthogonal subspaces even. And so it's interesting that the model can actually use the same shared set of parameters to encode these different modalities, although it does seem to keep them kind of in separate subspaces. The layer-wise analysis that we did showed that these 12 encoder, like implicit encoder layers, have a lot of similarities with models that are well known, like Hubert, Wave2Vec, Wave-LM. They kind of learn a similar progression of information from the acoustic signal. We haven't done similar analysis with, the image encoder, but that would be something I think would be very interesting to do. We also do see some interesting differences, though, with respect to these existing encoders. So, for example, we see that the first few transformer layers, because it doesn't have a ConvNet waveform encoder beforehand, it basically spends those layers just re-implementing the MEL filter bank pipeline with a lot more parameters. And then we see this interesting sharp increase in similarity with sentence embeddings starting at layer 10. Okay.
You have a quick question?
Yeah.
For your first
sure.
observation, basically about the modality-specific encoders, how much this could be also influenced by positional embeddings, which are necessarily the same?
Yeah, so that's a great question. The reason why in this analysis I didn't just encode the audio with no image and no text is because you do have sensitivity in the model to position.
But here the position is always the same, right?
Yeah.
Because
So if you basically control for the image size and the length of the text, then you can keep the positional encodings the same. And when you do that, you see this invariance. But if you don't do that, then the position encodings of the audio input are going to be different than what you would have gotten if you fed them in with context. And so you will not see, I mean, basically you'll see this similarity is a lot less than 1 because you're seeing the difference in the positional encodings.
And we just see the exact same drop-off, let's say around the layer 12, if you do so.
So I'd have to I'd have to dig up the plot again. So I don't want to comment on that without having the plot in front of me. But the similarity starts much lower just due to the difference in positional encodings. Yeah, so that's why we controlled it this way.
Okay, thank you.
Yep. Okay, so if there's no other quick clarification questions about this, then I'm going to move on to the wrap up, and then other deeper, more discussion-oriented questions on any part of the presentation we can take after that. Okay. Yep. Okay. Well. Okay. Well, I'll be quick. So the accomplishments that our team, kind of compiled from this workshop is that we developed this evaluation methodology using lightweight encoder-only evaluations to predict heavyweight multimodal LLM evaluations. And we also looked at using brain signal prediction and LID as task-agnostic encoder evaluations. We looked at generalized multimodal encoder training, where we were looking at training unified and robust speech general audio encoders, as well as encoders that could take as input images, text, general audio, and speech, all within one model trained together. We also looked at exploring the design space of different tokenization and segmentation methods applied to audio. So we looked at continuous time extensions of CTC. We looked at the interplay of text and speech token alignment. And as we also looked at how the different tasks that you could imagine solving with your audio LLM are going to respond differently to different types of tokenizations. And then we followed that up with some analysis of a recent encoder-free model. So we learned some really interesting lessons. We found that heavyweight evaluation was far more challenging than we predicted. It turned out that the stock LLM backbone that we were using to anchor our heavyweight evaluations already got 42% accuracy and placed 13th on the MMAU leaderboard when you just give it random noise. And despite that, we spent a lot of GPU days across, a large number of GPUs. You probably all saw us using the skipjack cluster disproportionately, perhaps. no single heavyweight model that we spent all that time training was able to beat that baseline. And so for that reason, the results for the lightweight to heavyweight evaluation remains inconclusive, although we did have lots of nice results on predicting lightweight evaluations using things like brain encoding performance. When it comes to training multimodal encoders, we found that distillation of non-speech and speech encoders into a single model works really, really well. We can further improve the performance of those models when dealing with overlapping speech and non-speech audio by using robust training techniques. We found that brain tuning, so actually using the brain prediction task not as a diagnostic, but as a objective for training the model, actually works really, really well. And we saw, especially for video and audio-visual tasks, you can take an encoder, do some additional fine-tuning on it, predicting brain signals, and it suddenly gets better on a whole bunch of other video understanding and audio-visual tasks. So that was a very, very awesome result. We also saw that unifying encoders across different modalities shows some promise. We saw evidence that if we have sort of modality universal general knowledge encoders working in tandem with modality specific experts, that we saw in some cases a factorization of shared knowledge versus domain specific knowledge. So we saw the speech experts focusing on doing things like speaker ID, whereas the general knowledge encoders focused more on doing things like speech recognition because they were also being trained with encoding text. And we also showed that this kind of unification and parameter sharing also in many cases allowed us to outperform the teachers or get close to teacher level performance, but with far fewer parameters. Finally, looking at multimodal tokenization, we had some really, really cool results here showing that we can aggressively downsample speech and audio representations to as low as a 3 Hertz frame rate without hurting performance on a range of speech tasks that require different levels of reasoning at either subword or utterance level. And sometimes we even saw performance improvements by doing this very aggressive downsampling. Fixed length pooling worked surprisingly well, much better than I thought it would, but linguistically informed oracle boundaries are even better, which implies the existence of learnable tokenizers that are variable rate that can do better than these sliding window based approaches. And we have some preliminary experiments using reinforcement learning as well as CTMC to start learning those variable rate tokenizers. We also looked at the interplay of audio tokenization and text tokenization within the same LLM, and we found that this matters a lot more than you might think. We all take BPE for granted. We just assume this is the right tokenization to use, but it turns out that we can BPE is almost always one of the worst text tokenizations to use in the experiments that we ran, looking at things like stress detection and ASR. And then finally, the CTMC framework that Matthew presented provides a nice way to do inference time scaling of the token rate for different tasks. And like Matt alluded to, I think it'd be very, very cool to kind of close the loop on this and say, well, depending upon what the task prompt is, we're going to take a guess what you want to do with the audio, and we're going to set the downsampling rate accordingly. So there's some open questions in future work that we're going to be looking at. So I think the evaluation question here is still open, whether we can use lightweight evaluations to predict heavyweight evaluations. It remains inconclusive, but I think we all still kind of believe in our hearts that this should be possible to do, but it's just very, very, very expensive, time-consuming to do these heavyweight evaluations. We probably could have spent the entire workshop working on getting one model working, and it may not have worked. Along the way, though, we developed a wide range of really cool, novel, and extremely promising techniques for improving multimodal and audio encoders to be integrated into these LLMs. And so post-workshop, we plan to scale these up, perform more comprehensive evaluation, and write a whole bunch of papers about these new models that we developed. So we want to say thank you to the workshop organizers and everybody that made this possible: Sanjeev, Paula, Ruth Scully, Karen Collins, Dan Mead from CLSP, JHU DSAI for providing computational resources, as well as the Skipjack sysadmins for working with us as we stress tested their system, the JHU Whiting School of Engineering, as well as the CLDT team, and the funding agencies that supported this workshop, including the NSF, COE, Google, NACL, Amazon, and the CLSP. We had a ton of fun this summer. Here's just a couple of photos from our team. We had 2 birthday parties on the same day. We had visitors, old friends we hadn't seen in a while coming down to see us, like Bowen, and we enjoyed all the outings with the rest of the workshop participants. This is at Captain James Crab Shack that we went to shortly before it unfortunately had a fire. So if you're still in the mood for crabs, you can go to LP Steamers instead, perhaps. Okay, so I know we went way over, but if there is any time for questions, we're happy to take those.
Okay. Sorry, David, it's still way over.
Okay. Oh. I mentioned I thought it would be to be a bit over.
It's all right. I mean, there were questions also, so this was a burning question there.
So JSOT is coming to an end, finally, right? For some of you, not for us. It's always a pleasure to have you here.
You need a PowerPoint from this one. Do you have it on that one? It's just the battery's dead for this.
While we're waiting, I just wanted to make an announcement. There were a couple of questions, people asking if the slides of these talks will be available, and it's mainly for the online audience. Yes, maybe sometime in the next week, we'll get all the final versions of the slides people used and put them on the JSOLT website. So slides will be available over there. And while we did stream everything live, we'll do a little bit of work to do some post-editing afterwards, and the videos will also be there on YouTube. But I don't want to promise a time for that. I think, Paula, it might take a month or so, right? Because whenever the CLDT team has time, we'll get to it and clean them up a little bit. So videos in a little while, slides next week.
Okay, it's time to wrap up, guys. How are you feeling? Tired, right? So it's always a long preparation journey getting to this point. And okay, yeah, so the journey starts in September. That means next week. So Sanjeev usually starts this journey. He's the main person, and we end up with this nice day when all of you are tired, but hopefully very, very happy. I hope so. And there's like some to-do list. Some potential team leaders, we are waiting for your proposals for next JSOT. I think we are doing next JSOT, right, Sanjeev? Hopefully. So usually we hope to have the proposals early October. So if you have somebody in mind, send us an email. The sponsors, please continue your support to JSOT. If you have any sponsors, please talk to Sanjeev, okay? And where does the mystery? Well, some of you know some things, some others don't. Ask Sanjeev, okay? Everything goes to Sanjeev. And then this thing is not working. Okay, so first I want to thank all the instructors in the summer school. We have a bunch of them. You already know them. I don't want to mention because I'm sure that I will miss some people, but it was great to have all of them, including some of the team leaders. And we had this wonderful workshop calendar. Of course, the most important thing here was probably the ice cream and the cookie break, where all of you socialized and had fun. And today we are having like great presentations, and it is a pleasure to have you here all the time. So first of all, I want to thank all of you, J Salters. Thank you for coming here, for enjoying and for being part of this effort and research. So thank you so much. So you're the main players of this workshop. And then I have to thank all our sponsors, the COE, the Google, DeepMind. Where is Pavel? Okay, yeah, because we needed some support for the summer school, and he was there saying, yes, Paola, I can give you credit. So it's like very, very nice. Amazon, the AI, NSF, NACL, also for supporting the summer school. I'm gonna skip these ones except the Whiting School of Engineer for the facilities and everything, because for the others I have pictures. So thank you, our staff. It comes like little by little. Karen, Myra, Ruth, Nicole, Kim, Edmund Washington, Dan, our sysadmin, Dino, that is in charge of all our social media. Big thanks to them, please, guys. They are not here. Some of them are preparing the stuff for the farewell dinner later, okay? So yeah, be there, please. It's gonna be a lot of fun. We are preparing a lot of things there. And our nice students, Harshada and Krishita, please stand up. And they are super, super wonderful. Yeah, all the time, being ready, okay, with coffee, tea, water. I don't like this tea. Yeah, I don't like these cookies, right? I prefer these ones, yeah. There's lots of stories behind the scenes. So we really thank both of them. And of course, our CLDT people, yeah, back there. Always making my dreams come true with the sound and everything. Brandy's not here today, but she's the main person. But also Drew right now is our captain, right? And of course, Marshall over there is always supporting us. Thank you so much, guys. It's always a pleasure to work with you. And of course, the skipjack and the CLSP grid that I know that you're still using it. I checked them, both of them this morning, RJ. Yeah. And probably Jessica, Roger, and other people. Okay, I checked. And I really want to thank these people because they are always an example to all of us. And we are like following their steps. Frederick Jelinek and Jack Godfrey from heaven, okay? And of course, the mastermind of this workshop, okay? Sanjeev, whoa. Oh, yeah. Thank you, Sanjeev, for making this every year. Every year since September, we start this journey, and it's thanks to him. Okay? Thank you, guys, very much. Thank you, guys. You will remember me by saying, do you need anything from me today? Right? Okay, it's always a pleasure. Okay, now enjoy. I'll see you at the farewell dinner. Be there, okay? 6 p.m.